And through this materialize the Danish Water Days. And I'm, of course, very happy from the Embassy of Denmark in Ukraine to be here today, to be part of the Lviv Eco Forum. Thank you very much. And do also visit the stand of Danish companies in the exhibition area. And thank you so much for the very good program of the Lviv Eco Forum. Thank you very much.
Михайло Хенсен, ваші оплески і передаємо йому слово.
First of all, thanks to Water Association for introducing us or incorporating us in Lviv Eco Forum. The next 2 days, we will take you through water in society. We will start with the groundwater and then go via distribution. And tomorrow, that will be today, we talk about clean drinking water today. And tomorrow we will talk about wastewater, how to collect it, how to utilize, how to clean, how to utilize the potential in the wastewater. So we see wastewater as a resource instead of a problem. Just excuse me, very briefly, Denmark is 100% based on groundwater. So that is why we will start here today with groundwater, how to abstract, how to secure, and how to make sure it gets to the consumers. Thank you.
Danish Water Days офіційно відкрито, тож беремось до роботи і до навчання. Вітаємо вас, друзі.
And first panel will be about groundwater. So we have some groundwater experts coming to panel 1 here. It is Jesper Hannebanesen from our Danish EPA. It is Peter Thompson representing the companies that find or map the underground and find the groundwater. And last participant in this panel will be online from Denmark. He is a software supplier transforming the data from these this underground mapping into 3D models that you as a water utility can use to know how much water we have. So I will give the floor to Jesper first from Danish EPA.
First of all, I want to say I'm very honored to be here and happy to be here and very glad to see that so many people showed up. We have a presentation from Denmark about groundwater management. So I can start telling you who I am and what I'm working with. I'm from the Danish Environmental Protection Agency, where I'm head of the groundwater division. And in Denmark, we have about 35 people working at the EPA with groundwater. And as Michael just said, that we are 100% reliant on groundwater for drinking water. And I think that's very important to say also. So that means that everything that comes out of when you open the water in your house, then all the water is from groundwater. And that's very important. And another thing that's very important to say is that, and I get to it also on my next slide, but we rely on clean groundwater for drinking water. And that means that we want simple cleaning. So that means that we do aeration and we do sand filtering. But advanced filtering or cleaning, we do not do as a standard. So maybe I can change. Yeah. With this slide, I just wanted to show why the focus on groundwater in Denmark is very important. This shows a survey made in 2016 where people were asked, what of the following Danish environmental problems concerns you the most? And you have climate change. That's a big one. That's the green part. It's about 30% of the answers said that's the biggest concerns. Other things was extinctions of plants and animals, air pollution, harmful chemicals, pollution of seas, and so on. But the second largest one is pollution of drinking water. So in Denmark, and I think in Ukraine as well, it has the public's focus also. So that's also what I want to say, that it's very important also to the public what we do in our daily job. So that's very motivating, I think, that people care about what we do. So this is just a timeline about the history of the groundwater mapping that we do in Denmark. So basically in Denmark, we started in 1998, where politicians agreed on that we need clean groundwater for drinking water in Denmark. So we started groundwater mapping more than 25 years ago. And then in 2000, the year of 2000 was a very important year also, because what we learned through the years is that one thing that is very important is that you need guidelines and procedures how to do equally groundwater mapping every time when we start a new area. So that's very important, and also for documentation and so on. So it's possible to see what we do. Then in 2007, we started what we call protection of the near borehole areas. So it's a targeted protection, and today we have special legislation in the near areas of the boreholes. And then in 2015, so that's about 15, 20 years after we started the groundwater mapping in Denmark, we mapped the whole country. So that means we mapped around 40% of the country where all the groundwater resources are. But we're still standing here today, and that's because we have water utilities when they make new boreholes or have water extraction from existing boreholes where we need to extract more water or something like that, then we do some further mapping also. So we have continuous operational maintenance task today. Yeah, next one. So this is just, I don't know how many of you know how the Danish structure is, but we have on the left side, we have the Danish state, so it covers the whole country. And it's also including the Danish EPA, where I'm working, and we do legislation, orders, guides, approval of pesticides, and then of course groundwater mapping. Then we have the regional governments. We have 5, soon to be 4 regional governments in Denmark, and they're responsible for mapping and monitoring polluted sites in Denmark, and then also cleaning polluted sites. So that would be industrial polluted sites mostly. And then we have the municipalities. We have 98 municipalities in Denmark, and they're responsible for water supply, water permits, wastewater treatment, and planning and action plans, and so on. Yeah. So when we talk about groundwater mapping, this is a coastal profile with a picture taken from a coastal profile in Denmark. And because the problem with finding groundwater is that it's difficult to see where we have water in the ground beneath our feet. So this is, I'm trying to illustrate what we're looking for when we do the groundwater mapping. So what we look for is we have sand aquifers, sand or coarse gravel aquifers, where we have layers, geological layers, where the water is able to move. But another very important thing is also that we have clay layers. In Denmark, most of the upper geology is quaternary geology. So what we're looking for is, meltwater sand, but also clays moraine, where we have the possibilities to have some protected aquifers. So basically, we want to see how are the water moving from the terrain down to the aquifers, because then we know where to place the protection of the groundwater. So this is just to illustrate what we're looking for, but how we do it in the groundwater mapping program, if you can take the next one, is that we have borehole information. So this is an example, just a conceptual model of boreholes. We have clay, sand, coarse gravel, clay, and the same on the other side. If you could take the next one. Yeah. And in between, we collect data, like geophysical data. And I know my colleague from Denmark, Peter, is going to show some real examples later, but this is geophysical layers. Basically, we're trying to see if we can look into the ground without drilling boreholes to get information. So what we get with the geophysical data is that we can measure the resistivity. So in areas where we have high resistivity, we can correlate that with the boreholes, because we know high resistivity is mostly sand and coarse gravelly sediments, and then the more clay sediments have a low resistivity. I'm sure that Peter is going into it further on. And then we can correlate the boreholes and the geophysical data and interpret a geological model. So if you take the next couple of slides, so you see the black line, we try to correlate how the geology is. Next. Yeah, and the next one. So what we see here is we have a sand layer, which is the aquifer, and then we have some clay layers, which is acting as a protection for the aquifer. Take the next one, and then we can correlate to reality. This is this is a very fun picture. In the real world, it's not often this easy. So what we do is we do different surveys, like we do boreholes and we do the geophysical mapping, which could be SkyTEM systems where we measure in big surveys, but we also have ground-based surveys. And then, of course, we take all the existing data we have from boreholes, like chemical analysis and so on. We have a public database where we can extract all the data and build a geological model that later we put water on it, and then we see how the water flows. So what we are interested in is to see where is the groundwater recharge and how is it entering the groundwater aquifers and the boreholes where we extract water. When we do this work, we have, of course, people employed at the EPA, but we also have a very close cooperation with the Danish private consultancies, different companies, but also with the Geological Survey of Denmark and the Danish universities. So there's a big cooperation, both parties who's conducting all the groundwater mapping, but also to all the stakeholders like the municipalities and the water utilities and so on. So next one. So this is just a picture to show another thing that we see as that has great importance in Denmark, is that we have a very decentralized structure, water utility structure. So what you see on the picture is actually we have all the catchment areas from or to the boreholes where we're extracting water. So in Denmark we have about, I think it's close to 2,500 different water utility plants, and we're quite a small country, as you probably know. So we're around 4.3 million hectares with a lot of water utilities. So it's very decentralized. So that's also a way to keep a good resource and sustainable water resource in Denmark. Of course, we have in areas like Copenhagen and so on, we have a resource that is where we have a lot of extraction. So in some areas around bigger cities, of course, it's complicated. So, but what we're looking for here is, when we do the groundwater mapping, is where to place protection. So Denmark is about 4.3 million hectares. And I've written a lot of numbers up here and the different kinds of focus areas we work with. Maybe if you can take the next slide. Next slide. So what I want to show with this is just a quick overview of what we're working with. So this is just like an aerial photo of you have a borehole, the yellow one, where we have a near borehole protection zone, and basically all the municipalities and water utility plants have to assessed if like pesticides and nitrate and so on are allowed to be used in these areas. Then we have a larger area, which is the catchment area of the water utility. And within this area, we do a vulnerability assessment for nitrate. So one of the main concerns through the last 25 years in Denmark with the groundwater mapping has been mainly focused on nitrate, because we know how nitrate reacts on the way down to the aquifers in the ground. But today, of course, we also know that we have other problems like pesticides and other difficult chemicals. Yeah. So if you take the next one. This is just showing some areas where we do groundwater protection. And the map, what it shows is that we have areas with restrictions. And if you take the next one. So this is just, you see an aerial photo. You see the green and the yellow areas is where the municipality and the water utility made agreement with landowners not to use either pesticides or nitrate or both of them, and planned areas. And what you also see, I know it's a little bit difficult from down there, but we have some areas with forest, but we also have areas where we still have farmers, growing corn and so on. And it's still possible, but we compensate the farmers not to use like pesticides or nitrate and so on in some way. So that's the water utility plants and the municipalities who's making agreement with the landowners. And I've written a number, I just looked at it last night, how much groundwater protection, how far are we in Denmark? And I could see that we had a little bit more than 8,000 hectares in Denmark protected either by pesticides or nitrate. And some say in Denmark that we need protection of 200,000 hectares. So we're a small step on the way. So, but now because we have had the focus on nitrate mainly on nitrate for the last 20 years, the focus both for other chemicals, but also to speed up the groundwater protection. Our minister gave us a new task about 2 years ago, where we want to find the areas where you could say you get the best payback for your investment when you do groundwater protection. So maybe you just go one back. So what we've been looking for the last 20 years is how are the water moving into the aquifers from where we extract water. What we're looking on today is also areas where we have water coming into, this is supposed to be a conceptual borehole where we extract water. So the focus today is also where do we have large groundwater recharge, large amount of water coming into the aquifers and getting pumped. So we're looking at the amount of water, where do we have the largest amounts, but also how fast are the water coming into the aquifers. So these areas where we have large recharge and young water coming into the boreholes, that's what we are looking for in the future also. So within these larger areas where we need groundwater protection, we try to focus on the areas that is, you could say, most vulnerable. And then the next one, I know what the next one is. So it's, I just want to show that something we work with for many years is also how big is the resource in Denmark? How much water do we have in the ground? And a couple of years ago, we made together with the Danish Geological Survey a study of how much water do we have and do we have sustainable water extraction. Another thing that we need to look at is how much water do we need in the future. And in Denmark, it's a little bit difficult because we made a report on the right side. When we look for the back into the last 20, 25 years, we had a raise in population from about 5 million, and today we are about 6 million people in Denmark. So we are a small country compared to Ukraine also, but we had a raise for about 1 million citizens in Denmark. And when we look at the water consumption for drinking water, then we see different trends. So the water consumption is going down, and that's because people are very good at saving water. And we started back in 94, I think it was, we started paying for our water also. And so the water consumption has been going down for the last 20, 25 years also. So we have a trend where we have a growing population and the water consumption is going down. So now we're looking at how much water are we going to need, how big a resource do we need in the future for drinking water consumption? And that's a little bit difficult task. I think that was the last slide I had.
So thank you. My name is Peter Thomsen, and I work at the nearest Danish consultancy company, and I'm a geophysicist, and I've been working with groundwater mapping for the last 25 years, mainly doing geophysical investigation as part of the groundwater mapping, where we do, as Jesper said, large-scale geophysical investigation combined with boreholes and other informations to evaluate on the hydrology and hydrological conditions. So it will be more technical presentation than Jesper's, but I guess you will learn something about how we use geophysics in Denmark. So I will first go into the history behind using these geophysical methods for the groundwater mapping in Denmark. We have been using it for the last 40 years, so I'll come back to that. And then just 2 slides about the theory about the method that we use, mostly the transient electromagnetic methods that we use. And then I'll give a short presentation of 2 system providers that provides Danish companies that provides high quality standard geophysical systems for groundwater mapping. And then I'll show some cases from 3 projects that we have been involved in. As Jesper mentioned, we are highly depending on the groundwater. We are not using any surface water for the water supply, so we are highly depending on. And for geophysics, since we started this geophysical investigations like 25 years ago, we have been reporting all the data to the national database. So what you see there is a picture from a national database that includes all the geophysical investigations that has been done during this groundwater mapping program. So when we began the groundwater mapping program for geophysics, we used this standard resistivity methods where you inject current in the ground and measures the resistivities. But in the 90s, new systems was developed, and especially this TEM method, transient electromagnetic method, that I will explain later, has been used for the last 25 years since the mapping program began in 89. And it's much more efficient than doing the standard resistivity measurements. And as Jesper mentioned, in 1998, the National Danish Mapping Program was initiated, and that to ensure and protect the groundwater resources. So since 1998, we have been intentionally covered these particular value areas that you can see marked as blue on the other map. Because we needed to collect a lot of data at the University of Aarhus, they were developing a system that could be carried beneath a helicopter. Until 2000, it was only airborne systems that was designed for mapping raw material or for mining exploration. But at Aarhus University, they developed a system that was much more suitable for this groundwater mapping program. And in 2004, this became a spin-out company. And is now a private company called SkyTem Survey that does surveys on all continents. And the development in Aarhus University keep going on, and in 2015 they developed a system that could be pulled behind a ATV that could cover also large areas in faster times. And in 2020, this also resulted in a spin-out company called Temp Company that develops these systems that we use in Denmark. And now Temp Company is still developing other systems. So you can go up to the booth afterwards. We have some brochures from that company also. So back to the theory about the TEM methods. As I mentioned, it can both be ground-based, it can be pulled array, and it can be airborne. And it works like that you need a transmitter, and you need a transmitter loop, and you need a receiver coil. And by injecting current in the red coil, you introduce a primary magnetic field in the ground due to Earth's law. So this magnetic field induces a current in the subsurface, and this current, due to Faraday's law, results in a secondary magnetic fields that you then receive up in the receiver coil. So it's so you don't need to have a direct contact to the ground to do these surveys. So you can do it from the air, and you can do it pulled by pulling the system. And what you get out of these soundings is a sounding curve where you get a decay curve, and then you do some geophysical inversion. And the output will be a resistivity model with depth. And now I say resistivity model, and the resistivity says something about the conditions in the subsurface. Low resistivities indicates clay sediments, and higher resistivities indicates more sandy sediments and also aquifers. So by mapping with this method, we get an idea together with boreholes what the conditions are subsurface. And yeah, so I'll go back to just to shortly introduce these two spin-out companies that was based out of the innovation that was done in Aarhus University in just after 2000 and until now. So for SkyTem is a private consultants doing surveys. As I mentioned, they're spin out of Aarhus University. They've got approximately 100 employees now, and they're operating on all continents, doing groundwater investigation and mining explorations on all continents. And as you can see to the right, we have the transmitter coil up here and inducing this magnetic field in the ground and receiving again in the receiver coil up, which is located up here on the tail. So it's in fact the same as I showed before. It's just hanging on a helicopter, or now it can also be hanging on a drone, because they have different systems. And we're going from right to or left to right, increasing depth of investigation. So the diamond system is a newly developed system that is quite small and can be carried by a drone. It's only weight 50 kilos. So a drone can carry it. And then you have the other systems that are used for primary groundwater investigations, and the last one, the 312, is primarily used for mining explorations. So they have the different systems that they can adapt to a mapping. And to the other company, this I mentioned this temp company that's also a spin-out company from Aarhus University. All the development that has been done there within geophysics, and they develop ground-based, high-resolution systems, and both continuous and also single-site systems. So these systems are ideal for smaller and mid-sized areas that needs to be covered. And as we use it often as a proof of concept before we set up a large SkyTem company, SkyTem survey. We do some single site soundings to see what we can expect for resolution of the ground. So I will show some results from 3 projects that we have been involved in. The first one is from Morocco, where we used this SkyTem system and single site system from a temp company. So the pilot, this is Morocco, and this basin is Tensift Basin, which is one out of, I think, 8 large administrative basins in Morocco. And the pilot survey, the pilot project that we were doing is located where you can see the white marked here. So just on the foothill of the Atlas Mountains. And the purpose for this project was to map the conditions of the subsurface and to do some data collection for the groundwater modeling. Now here you see the elevation of the area. It's slightly dipping towards north, so it's elevating 400 meters from south to north, and up in the north we have this source which is dry. So it was also to see where the water from the Atlas Mountains, where it disappears in the areas. There's a lot of farmers doing abstractions in the area. And the geology, I should mention that the area is just here on this profile called Profile 4. So we have a geology going from south to north, where we had some dipping layers. And especially the light green is this limestone that we are looking for as an aquifer in this area. So this is just a geological setting in this area where we are looking for this limestone and this Turanian limestone also, which is quite deep. First, to do this proof of concept, we did 1 day of surveying in the area, doing 12 of these single site soundings, where we collect data on the ground to see what we could expect from the resistivity models in the area. So the purpose was for this day of fieldwork was to map close to 4 known boreholes and to see if we could resolve the layers that are described in the boreholes. And this is, in fact, also from one of the soundings where we can see the transmitter coil here and the receiver coil in the middle. We're standing here collecting the data, and the data are collected by using an app on a tablet. So you can use any mobile phones or tablets to collect the data from the system. And what we got out of that was that we got 3 soundings from this site 1, where we can see the borehole here in the middle, and the TM sounding number 1, 2, and 3 here. And then this profile is shown from the southwest to northeast, showing these 2 soundings up here, the borehole and the sounding number 1. And down here you can see the curve. As I mentioned before, you get the decay curve by doing these soundings, and you can see that the decay curve is much longer here for sounding 1 than for the other soundings, and that's the reason why we got a deeper penetration here. So at this site there was a better signal to noise level than at the other 2 soundings. So that's the reason why this is looking deeper, the sounding. And if you combine with the borehole, we can see that the top layer correlates with this conglomerate that's in the boreholes, and that the low resistivity layer is correlating with this layer that is mostly clay. And then we have a higher resistive layer in the sounding 1 that correlates with this limestone that we are looking for, this topper limestone. And then we have some marl down here that also results in this low resistivities. So we could see that there's a good correlation between the borehole and the resistivity, and that gives us good opportunities to see what we could resolve with the SkyTime system that we did afterwards. So doing these small surveys to pre-investigate what to resolve in the larger surveys. And the larger surveys here, this SkyTime surveys were collected along lines with a distance of 250 meters going west to east. And in 7 days, they are collecting these 2,000 line kilometers. So you can see the system here and how it's carried in the area. And for that, we are using this 306 system that is the system that is mostly used for groundwater mapping. And often we show these results as resistivity maps and resistivity sections. So here you see the resistivity in elevation 900 to 920 meters. And so you remember the area was dipping towards north. So it's only the sounding to the far south that is including in this map, because all the other areas are below this elevation. And this is a model section going from A to A mark, going from south to north. And now we go down. You can see up in the right corner, we are going down through the different layers, and you can see now that we are in an elevation area that shows up here. So this black line shows where we are in the elevation along this profile. So going down, we see that more and more data are included in the resistivity maps. And you can also see that on this profile is still most of the profile is below this elevation. And going, we see that that now this quaternary sediments are showing up as a high resistive layer here, and correlates with this layer, this high resistive layer in the middle of the area. And now we are going further down. Now we are in elevation 600 meters, and moving down the model section you can see on the bottom. And if I can go deeper, now we're getting into an area where you can see the marl here coming in as a low resistive layers, and you can see the marl coming in from on the model section here as this Eocene marl, and then we have the Eocene limestone that we have here, and then there's this Senonian, another marl that is below this Eocene limestone. And this section, you should remember, is this line, so we only see this Eocene marl on this model section. And going further down, we see this Eocene limestone, which is the upper aquifer in the area, covering most of the area here along this model section. And if you can see, this Turanian limestone shows up at the north side of the profile. It can be this area with higher resistivity and the low resistivity layers that is indicates this Turonian limestone. So now I think I'll just move further down, and we can see this Eocene limestone is, and then we have this Senonian marl, and going deeper. Now all the models, we reach the depth of investigation, so we don't have any data from below here. So that is how we can present the data as mean resistivity maps and on model sections. And then based on the results from this, just moving down, and now there's no information from the geophysics. And you can see here that I've done some interpretation of the section where we have this marl here and the Eocene limestone, where it's difficult for us to see the bottom of this Eocene limestone here. And then we have the Turanian, the deep aquifer, slightly, we can see it maybe up here, and it's going beneath this Eocene limestone. So it will be down here. And then we have this Senonian marl showing up here and have a slightly higher resistivity up in the south section. Yeah, so this was just the Eocene and the Turonian marl or limestone. And then to another project where we use this small system from SkyTem, which was this Diamond Tem, which is a system that only weighs 50 kilos, and for that survey was carried by a helicopter. And the purpose for this investigation was to investigate if there was any effect from new extraction wells on a protected nature area in the area. So we have as I mentioned, we both did some TEM with this pulled array system from this Temper company. We did up here in the forest, and then we did this drone TEM measurements here around the protected area. So the protected rivers are down here, and the utility are exploring the possibilities to do abstractions up in this area. So we need to have the hydraulic conditions between this area up here and the protected nature. And as you can see, the system here, it's quite small when it's on the ground. It's only 5 meters times 5 meters, I think. And as I mentioned, it for this survey, it was carried by a drone here. So the drone is flying up here, carrying the system. And what did we then get out of this? Is the investigations. As you can see on the bottom here, you see a model section going from south to north up. You can see the sand layer correlates with the high resistive areas here. And as you mentioned that where it's marked with the black, it's data from the drone TEM, and where it's marked with orange, it's data from the TTEM survey. So you can see that there's a really nice correlation between the results from the two methods. And we were happy to see that. And in this area, the aquifer is this layer. So we needed to investigate if there was a contact between this aquifer down here up to the protected nature area up in this part of the profile. So we could see that there could be a contact with the clay. And this is the next profile where you can see some of the observing wells where we have this sand layer, which is the aquifer, more or less correlates with this high resistive areas. This data is from the drone TEM and this is from the TTEM. And then you can see this clay layer in this and here it correlates with this lower resistivity. Again, you can see that there can be a connection between the river and the aquifers. So again, just another profile. So by doing that, we could say that there might be a possibility that there is connection between the wetland up at the protected area and the injection or the abstraction wells. And the last case that I have is just a case where we did some TEM, and you can see here we have a model section with a geological model that has been done during the last 20 years, from going from west to east, where we have this tertiary clay, which is mostly clay, and then we have this quaternary sediments up here. So this model is based on modeling both with the geophysics and boreholes and other data. So in this area, they needed to have improve the hydrological understanding in this area around this distop. So it's located just here. And as I mentioned, we did TTEM. And here you can see it's 5 days of field work, and you can see some data from existing SkyTEM soundings here, and you can see the results from the TTEM surveys marked here. And this is this is elevation intervals going. You can see the elevation going down here. So now I'm moving down in the elevation. And you can see on this picture, I think it's this one, we can see that the areas have a high resistivity. This is interpreted as an aquifer in the area. Then we have some clay, and then we have the tertiary clay here. And if we draw, again, a model section going down, we can see the model section going from west to east, and we can see the existing boreholes. And you can see that this low resistivity layer correlates nicely with the clay in these boreholes. And then we have the sandy aquifers that disappears here, and the tertiary clay that are dipping towards west. And these are just sound data from the old SkyTem survey that we have plotted on the profile from down here, these two soundings. So now without these boreholes or without the geophysics, it was needed to do the interpretation of the geology without any information, but now you have the geophysics to do the interpretation. So if I put this profile into this geological model, you can see that it correlates nicely with the geology in the area, but now you get a much better understanding of the conditions just right here. So I think that was it. And you can visit the Danish booth. It's really nice. We have some brochures and some stuff from the companies and that you can get, and you can come to and talk to Christina and I about the geophysics. So thank you.
Hello, everybody. I'm sorry I couldn't attend the meeting in Lviv, but I'm happy to be here online. And I'm sure that if you have some questions, you can, of course, ask me during this session, but you're also welcome to ask Peter, who just presented, or Jesper Hannibalsen, who did the first presentation. I think they can stand in for me to some degree at least. I'm going to tell you a little bit about geological 3D models and data management in relation to groundwater mapping, as my colleagues has started on. I'm from a company called RGIS. We are a small software development company. Has been around for more than 20 years, and we are doing software on geology and especially 3D modeling systems for both data management and visualization. We're also doing quite a lot of research and development projects, but even though we are limited size, we have customers all over the world that has sort of tapped into the Danish groundwater mapping that we also are very involved in. So we have been doing these software developments for the groundwater mapping the last 20 years. So we're quite experienced. I has tried to do the math, but I think if you combine all the spending that has been done throughout the years, it's more than 400 million euro that has actually went into groundwater mapping, and it might be even more. Much of this money has actually been used to generate data that has been compiled into a 3D model, and that's what I'm going to talk about. So this all started 30 years ago. We saw some high nitrate concentration, and there was a search of good protected aquifers. And here in this figure, you see what we did know based on boreholes only. So we could see that there was some kind of depression here where there was a possibility to find a protected aquifer. This is only based on boreholes, and things didn't add up. So we started to look into what can you do, what can you do in order to get more knowledge on the subsurface, and the answer was geophysics, and that's where it all started. We tried to add geophysics to our knowledge. This is 20 years ago, so it was based on ground-based soundings, as Peter has mentioned before. But it really meant a lot. So suddenly there was something showing up here, a depression, a buried valley that made sense if we looked at what was possible what was possible in the water abstraction in the area. So with the addition of geophysics, we gained a lot of more knowledge, and I think that's the point of all this geophysical stuff that we are doing. It's a way to interpolate, you could say, or extend the knowledge you have from boreholes into a volume, into a whole area. But in Denmark, it was a way we saw the light, you could say, in this, and that spun out different developments of both technologies, measurements, how to do instruments and all that, but also software tools, and of course a lot of knowledge. Yeah, so the information has been extended by factors by using geophysics. Here is another example. That's how the national database of borehole looks like. Even though this looks fine, it's a 500 scale here, and there's a lot of boreholes. They might not be that deep, and there's a lot of places where we don't actually know anything. So by addition of geophysics, all the yellow dots here, that's flight lines from the SkyTEM system. We now have a very dense knowledge with 250 meters between the lines, and so it's the volume of data has risen by factors. So a 3D model is actually the backbone of decisions in general. You can ask, or you can look into the model, and you can, with these questions, what are the basins? Where are the aquifers? Where are the aquitars? How are they interconnected? Where is a potential of recharge? What are the volumes, and etc. All kinds of questions you can get out of this model. So in general, what's the groundwater resources? But also important, as we've seen before, it's important to know the vulnerability. Are there salt water coming in, maybe from below or from the coast, at least here in Denmark? Are there any pollution that could affect your water abstraction? So this 3D model is a basis for different kinds of derived products, like groundwater models, where you can actually calculate the volume of water you could get out of an area, but also different kinds of map products that can be used in planning, such as what to use the land for. Do you need to do some protection, as we heard about? Where would you build houses in the future? Where would you extend towns? Things like that. So the chain of mapping is like this. You should start gathering existing data and knowledge. Preferentially, they should be digital in some kind, at least. And then you could use that into build a preliminary model that actually shows what data you have, and you can visualize the situations and potential problems. With that, you can go to stakeholders and decide on if further data collection is needed, like for instance the nice geophysics we've talked about. It could also be borehole data. You miss some strict knowledge on the geology in some parts. And it's also important to say that you need to have boreholes. You cannot rely on geophysics alone. So that could be decided on the model. And when you then get these new data sets, you can add that to the 3D model, and you can get a much more detailed information on the underground. And I also think it's important. We've seen that in Denmark, that you need to integrate all types of data, all types of relevant data that you have. Not only boreholes, but also geochemistry. You need to take care of or take into considerations the geomorphology. How could a given area have been created? Wells, of course, and geophysical data. All of that has to be integrated into a single framework. And once you've done that, you have interpreted a geological model. You can get something like this. Yeah, and what we're using in Denmark is Geoscene 3D. That's the software that we are developing in IGIS, and that has been used throughout the years. I think the nice thing about using one single software is that it's very easy to communicate, and that has been the decision by the Danish EPA that we use a single piece of software, because then you know what you're doing if everybody is using the same 3D hydrogeological model. As I said before, we spend a lot of money in collecting data and integrating them into this 3D model. But when we started, we just started to do projects in different places in Denmark. So we ended up with a lot of models. I've written down here 250 models. 3D models were actually created. Actually, it's a lot more, I think, if you count everything. But 250 models were quite good, and all of these models has now been compiled into one national model. That was something that came more clear as time went by. You need to be able to manage this. If you have a model somewhere and it doesn't fit to the model next to it, it gave a lot of problems. So now it's compiled into one national, or on a way to be compiled into one national 3D model. And just to show you a bit on that, it's called LACOS, Large Scale Geomodel Manage and Collaboration System. So in Denmark, as has been told you before, we have many entities working on this mapping. It's both the EPA, but it's also private consultancies like Peter is presenting, that are actually doing mapping in Denmark. So it was important to have a system that could actually be used to manage that, and that's why we built this LACOS system. It's a web-based system where you can check out parts of a model, and you can revise the model, and you can check it in, and there's different kinds of QC procedures involved in that. So that's running, and that's how we are managing the day-to-day, or the year-to-year work in the groundwater management, groundwater mapping in Denmark. Another point is data management. So going from projects or model making, which is fine, which is it's a specialist case to prepare that. You need to have some systems to to manage your data. It's quite expensive to do all of this, and it's very valuable knowledge that comes out of all of this mapping and modeling, and lots of hours has went into doing that work. And that's where something like the GeoCloud, this is also something that we are developing, comes into place. It's a web-based system where you can host your data, you can do data management, you can provide access to data to both your colleagues or partners or the public if you want to do that. There's also a visualization part. So everything is there actually to do some decision making. So going from a specialist tool to a more general tool that can be shared by many. And just a few slides on or a few screen dumps from the system. There's a data administration part. There's many different kinds of data sets that are important in groundwater mapping that you can put into the system. And of course, there's also a user management system where you can assign different kinds of roles to users, from viewers to administrators. And here's a screenshot from the web map interface. You see a 2D map. You see this is actually some geophysical measurements that has been done here. It's a place in Germany near in the state of Brandenburg. But there's been some mapping done here, and you can see the data that are here in 3D, and you could also create, like these red lines shows you profiles, and you can do that in the web interface. So it's an easy way to access data and also model results. So if I should come with some conclusions, this 3D model is important that it incorporates all the data and knowledge. It's where you go to extract knowledge, and it makes that knowledge accessible. If you have to do collaborations, if you want to show it to stakeholders, politicians, or with other professionals that has to do something, maybe design a new water work or water abstraction. But it's also important that it must be maintained and updated when new knowledge comes in, and that's the ongoing process that we are doing in Denmark. It's not just a project and then that's done and you're fine. You have to keep on updating with new knowledge, and there's always new knowledge to be gained when you collect new data, a new borehole, and you have to revise the model. It's also was a base for decision and policies of land use, and very big investments could be relying on this. So it's my saying that the 3D model is the most valuable asset in the Danish groundwater mapping as such, because so much knowledge and time has went into it. And I've also done some thinking in relation to Ukraine and the situations you might be in. It's not that I'm too familiar to how things are in Ukraine right now, but my recommendations would be to compile existing data, to do digitizations if they are not, going from analog to digital formats, and store these data in a data management system to secure them and make them accessible. And then establish an initial model, as we've seen, point out the data gaps, where's more data needed. Are we in doubt of how things are looking down there? And then perform the mapping. And we've seen that by Peter doing geophysics, new boreholes, water samples, water chemistry, all kinds of things that are necessary, and then compile all that into a 3D model. So that could be the foundations for planning new abstractions, well-protected water resources, so that it's healthy to use the tap in the future. And my last point is that we have a lot of knowledge in Denmark. We have done this for many years. We've done mistakes. We've built all the tools, so we can help. That's my point. There has been some of this has come into play because we are doing a summer school of water, and I'm aware that several Ukrainians has now attended that summer school for some years. So there should be some knowledge to use from your colleagues in Ukraine. And finally, I want to say that the booth could supply you with more information if you want to. But I'm happy to take questions. But I guess we will wait for that for the panel. Yes, thank you.
Thank you, Niels Peter. Will you please be staying online for questions? So now we are open for questions. Yeah. Do we have a microphone more for the audience?
Yeah, thanks a lot for these presentations. We see that you are so highly advanced in all this 3D modeling and mapping. And for us, I would say, as for the whole water utilities in Ukraine, it's a fantastic, because we see that it's our future, but we also see how much money you spend to have it. So in this, I have two questions. First one, how much time did you spend to make all this system? And second one, I know that in Germany, for example, they have such kind of a rule that they are not drilling boreholes more than 100 meters down, because they want to save these deep aquifers for the future. So is it exist the same in Denmark, maybe, such kind of a rule, or you have enough water for now and for future? Thank you.
I'll take the first question. You mentioned how long time it has taken, and as also Jesper mentioned, that this has been going on for 25 years. But during this period, we have gained a lot of knowledge, so we could do it much faster now than we could 25 years ago. So all the development that has been going on makes it much faster to do all these things now.
So how you suggest, for example, if you would start to do it in Ukraine from the very beginning till the very end, how much time do you need approximately?
Yeah, for as I mentioned, it should be beginning maybe proof of concept if geophysics will resolve some of the issues somewhere, and somewhere in Ukraine it's sediments that are aquifers, or some areas it's more fracture zones in hard rocks. So it's quite easy to set up a pre-study to see if geophysics can resolve the problems, and then it's just to call SkyTem, and we talked to them just before we got here, and they can operate if you have the system that can carry the drone or the small helicopter that can carry the system. It's just a hook on. So for the small system, it needs a drone that can carry 50 kilos and maybe 100 kilos because it needs a little bit more, and can maybe go for 24 or 45 minutes doing survey. So it's just a hook on, so they can hook on systems that are here. And for the ground-based, it would be possible to move quite fast, doing some proof of concept of what we can resolve. And I think you will take the next questions. Was it?
Thanks. Yes, great.
Maybe I can have a few words more, because what we do in Denmark now is that we are taking existing groundwater mapping areas and then you could say remap them when we get new information, either from the geophysical data but also from boreholes. So what we do today is that we have areas that are maybe around 500-600 square kilometers. So it's you could say larger parts of Denmark, some of them up to 800 or 900 square kilometers, but it's not the whole country in one groundwater mapping campaign. But we have different projects running all the time, maybe up to 10 projects running at the time, where we have the geophysical data collection and the boreholes established and so on. But today in Denmark, we have a lot of data, existing data from the last 20-25 years. So if you look at our borehole database, we have, last time I looked, I think we have about 450,000 boreholes where we can extract data. So we have a lot of data already compiled from the last 20 years. And then if we look back from when we started in 98, the first 10 or 15 years, we almost didn't produce anything because we were inventing things. So we had the universities and the geological surveys and so on producing guidelines. How are we going to do the groundwater mapping? And we had the system like the SkyTem systems and other systems invented, and then we're using them today. So we had a slow start, but today we are compiling all the knowledge. And I would say today, when we start a new project in Denmark, we usually spend 4 to 5 years to do one project area. And that's including data collection. But after the data collection, we have the geological model and hydrological model before we finished. But if we should look somewhere else in the world, we have, I think both Peter and I worked on projects in California where they started from scratch. And I think they started in 2017, 16 or 17. Yeah, maybe actually later. They started talking about how to do the groundwater mapping. And today, I would say they're almost done. They need to put on the legislation and the regulation and so on. So that's about maybe 10 years. They did almost the whole state of California. And then they collected all the SkyTem TEM data and so on. But of course, they also had a lot of existing data from borehole. And then the question of as Peter had the slide where it said 400 million euros. I don't know if that's correct, but I know that we spend a lot of money. And how is it financed? It costs a lot of money. Yeah, that's true. But in Denmark, we have the water tax. And when we have the groundwater mapping in Denmark, for every time you open the tap and you have 1 square, or what you call a cubic meter coming out, the consumer pays it's about 0.03 euro cents. So it's really a small amount. So the consumer doesn't see it on the bill at all. But that's what finances the groundwater management in Denmark. So that's for the mapping part. Then when you need to do the protection, If you need to go buy up land to plant forest or whatever to secure the groundwater, then of course that's besides that. Yeah, and that's difficult to say how much it is. And then maybe I should say about the borehole, the depth. In Denmark, we have the municipalities who's giving the permit to water utility plants or farmers who wants to build a well. And that's local assessment and decision every time. So that's the municipalities who's giving the permits. And that's not the state, but we have what's very important in Denmark, we have education of the drillers. So we need to get, you need to have an education to be drilling boreholes and do it in the exact manners. And in the future, in not that long from now, I think in 1 or 2 years, we have a new order saying that you need to have a license to make the drilling. And that's a problem in a lot of other countries. I know that if you don't have a license, then you just make boreholes everywhere. But with new orders coming, you need to have a license. And if you don't follow the rules, then you'll have your license taken. So I don't know if that answering your questions. Yeah.
But can you clarify about this? As far as I understand, no rule in Denmark that you cannot drill deeper than 100 meters.
You have what the law that we are employed under is 250 meters, but that doesn't mean that you get a permit to make a borehole. You have a lot of areas where you're not allowed to drill, and you're not allowed just to drill and to extract water. For water utilities, they have to get a permit from the municipalities. A lot of areas you're not allowed to get a permit because of EU regulation, you're not allowed to disturb nature and so on. Yeah, so it's not an easy task to get a permit. Yeah.
Okay, thanks.
Oh, many questions.
Yeah.
Okay, first question: when you do geostudy, and you find aquifer, can you estimate a volume of water you get there? Same to oil when you do oil search. This is number one. Second one, do you see impact of when you find the aquifer near the seashore? Do you see impact of salt water in the sea on the fresh water that you find there?
Yeah.
This is number two. Third one, have you found aquifers below sea level in sea? Not to drill on a land, but in a sea. So if you, for instance, need to get water, but you don't have it on the ground, so maybe you can get from a sea drilling there.
I'm not sure if for the third question, I don't know if any boreholes at sea where we extract water, but I know that we have catchment areas going into the sea, so we have fresh water beneath the sea. But we don't have it. It's a little bit complicated it's a lot more expensive to make offshore drill holes, also like for oil industry and so on, than onshore. Onshore is a lot cheaper to make boreholes. And then for the salinity along the coastline, in Denmark we experienced the problem, but I think other places in the world it's a bigger problem. But with the geophysical method, we can see the saltwater intrusion, so we can also monitor if we have a saltwater intrusion coming into land. Now I mentioned California earlier, actually did some studies where we had geophysical data collected multiple times, so you can see the difference. Also, if you are pumping groundwater for drinking water, how much can you turn up the pump if you're extracting salt water? But I think in the future, saltwater intrusion is going to be a bigger problem because sea level rise and everything, and we have a lot harder pumping in some areas on the resource, so you get seawater intrusion also. And then to the volume of the resource, we try to calculate the volume of the resource. So we get, with the geophysical data, we can get the outline of the aquifer. And we can also see if it's sandy or gravelly deposits. From the boreholes, you can get further information about the deposits also, and then you can see what would the porosity be and so on. And when you have all these information, you can start calculating the volume of the aquifer, and then also calculate how much water is it possible to have in the aquifer. So, and how big a resource do you have? And then you can compare how much resource and how much pumping and how much rainfall and recharge are you getting. So that's, yeah, to have a sustainable water expression, you need to have the whole water cycle. So I don't know if Peter has anything to, and maybe I should say that the modeling part that was shown at the end here. So when you have the 3D model, that's when you can start calculating the volume of the resource. Yeah.
For the saltwater intrusion, I was doing also the survey in California, and in California we did offshore SkyTem measurements in Monterey Bay. So in fact, we also mapped the freshwater, what's it called, exclusion, the freshwater lens that went into the sea. And in California, they're using a lot of where they inject water close to the coast to keep the saltwater intrusion away. But SkyTem definitely gave a really good understanding of the saltwater, freshwater conditions there. And I know that also, I have not been involved in that, but in Holland, there are really, Netherlands, really good cases where geophysics also have added really nice value to evaluating the freshwater saltwater lens. So there are some, as you mentioned in Denmark,
maybe I should add that Peter shown the system that we use the helicopter and you can tow it behind the ATV and so on. But at the university in Denmark, they're also building a new system, like a stationary system. So you could almost dig it into the ground. And then it's monitoring. So it's like when you are measuring water level and you get data all the time, then they're building a new system. So you get a geophysical measurement, maybe daily or something like that. And then you can see the changes if you have saltwater intrusion.
Cool. And when municipalities, they give a license to drill, do they also specify what amount of water you can pull out of?
So if it's for drinking water, then you get a permit for a certain amount. You're not allowed to abstract more. I think it's not my area, but I think most of the time they look at so you have a threshold, so you get a permit for a higher abstraction than needed. So that's for looking into the future. So typically a permit is valid for 30 years in Denmark. So when you get a permit, it's valid for 30, and then you get renewal, but then it's also a bit higher than what you expect. So you have possibilities for the future also.
Thanks.
Thank you so much for your questions. We will now have a 10 minutes break before we continue with panel number 2, which is then we go more into distribution network. But before we go into the distribution network, we have a short introduction because we are, as you know, member of the EU, European Union, and Ukraine wants to enter European Union, which you will. but that also requires that you fulfill some regulation. So we will start with some EU regulation, and then we will move into water distribution. So 10 minutes break from now. Thanks. So we go directly into the distribution network, and now we will talk about DMA technology, which is district metered areas. Divide your distribution network into smaller sections, and then after that, Aarhus Water Utility and Lviv Water Canal will give you an introduction to where they are at the moment in their cooperation.
And first of all, thank you for letting me do this presentation. I am Claus Høgh, Senior or Project Director now with NIRS in Denmark, Danish Engineering Consultancy Company. And I've been working with non-revenue water and water networks, optimization of water networks for the last 25 years. And I've prepared this presentation here, which is about DMA technologies and IWA water balance model. What is the best practice approach and how to do this and what the advantages are. And it's just 10 slides, so it should take 10 minutes, I hope, maybe a little longer, but let's go. Managing a water supply network can be a tricky task, and with focus on non-revenue water management, what is the best practice today generally acknowledges that we want to have a structured sectioning of the network where we have to apply some monitoring. It's more or less built on the statement, what you can monitor, you can control, and what you can control, you can actually optimize. And if we start by looking at a traditional old school water supply system, we just have a very simple system. Water is being supplied into a network, and we have no idea about what is coming in. We have no monitoring. So all operation is based on experience. It's like empirical operation. But if we start to add some monitoring on our network, how much water we pump into or we supply into a network, then at least we will start to do we can have some global control of our network, and we can do some global optimization of our network. And if we take this a step further, then we will actually find out and segregate the network into some sections where we have a flow meter and a pressure sensor at the inlet to each section. And then we can actually start to find out what goes on in each of these subsections. So we can actually do a discrete control and a discrete optimization. So we can find the areas where we have the highest amount of non-revenue water, where we have the highest pressure, where we have the lowest pressure. So we can find out, depending on what our agenda is, then we can go in and do the right optimization in the right area. So that's the whole idea of implementing DMAs. Sounds simple, but it's not. It is a complex case to sectorize a very big water supply network, but there is a process to follow. There are some recommendations and some user guides from IWA that can be used. But in principle, it's a matter of starting by dividing the network into larger pressure managed areas. And then inside each pressure managed area, the pressure zones, they can be pretty large. And then subdivide these pressure zones into some smaller district metered areas where we know how much flow we are supplying into each of these district metered areas. And these are the ones called DMAs. And the pressure zones or pressure managed areas we call PMAs. So this is the overall principle of a sectorization of the network. And this is an example from one bigger high pressure or supply or production zone from Oslo in Norway, where the transmission system or bigger supply system for this supply zone looks like this. And after sectorization, it looks like this. So this is a translation into a sectorization. And if you have an existing network, that can be quite a complicated task to actually analyze this spider web of pipelines, especially if some of the pipelines are laid 40, 50 plus years ago, and only information is only available on old blueprints, paper drawings, etc. So it can take quite a while to do this accurately. The whole issue here is that it's important to have that each zone is actually well defined, that we know exactly how many inlets are to each zone, and all other entries or pipelines that could bypass the zone has to be closed so we can make accurate water balance, etc. inside such a zone, which is then the next step, the water balance. IWA defined this standardized version of how to do a water balance just about 25 years ago. And this is today more or less accepted worldwide as the best practice of doing a water balance. And it makes sure that whenever you work with water balance in one country and you get inspiration from other countries or other outsiders, everybody's talking the same language. This is how we do it. So that's a really strong recommendation. Don't invent your own water balance. Use this one. It works. I have now tried to use it everywhere from Malaysia to Denmark and US and Africa, and it works everywhere. And the main components when we talk non-revenue water are, of course, the real losses, which are the leaks in principle, and also overflows from water reservoirs. And there's a tendency very often when we talk non-revenue water reduction to focus on leaks, but in some cases, the apparent losses can be just as serious a problem as the leaks, because if we don't measure the water that is consumed by the customers accurately, or if we have illegal connections or unknown connections, then that may actually be bigger in some cases, in some areas, in some DMAs than the actual leaks. So it's evident that it's possible to somehow and somewhat accurately to calculate or estimate apparent losses and real losses. And then for the financial part, there's also the part called unbilled authorized consumption, which is more or less involved with or related to the billing system, but also to the operation. Do we have any authorized consumption that is legal in our network that is not paid for? Can we reduce that, or can we convert some of the unpaid into paid? Then that would actually increase the revenue for the revenue collection. So this is the whole principle of that. This total sum of these three is the non-revenue water. This many of you have most likely seen before, and we'll dig a little bit into this because it can be really, really difficult to determine from a desktop study the real losses, because that requires some field tests. So what we typically do is we have records from the inlet meter to a given area where we have the system input. And then we have data from the billing system, from the meter readers, data collection from meters and so on. So we should have a lot of information from that actually allow us to calculate all these subcomponents to the billed authorized consumption, the unbilled authorized consumption, and the apparent losses. And if you can calculate those based on the billing data and information about the customer meters, then we can actually use these subcomponents to calculate upwards, those, and we can then calculate all of the authorized consumption. And when we have that, we can calculate the water losses, which is the difference. Then we have to look into some estimation model for unauthorized consumption and customer meter inaccuracies. And this is a little harder than the first two, but there are some good models available that we can actually use to try to estimate the apparent losses. And when we have the apparent losses, well, then we can also calculate the best guess or best approach to the real losses, which is now based on a pure data study. The next step would be to include some field studies, field tests, to get some more knowledge about leakage. and this could also be from historical burst records and so on, to actually subdivide the real losses into how much of the leaks are on transmissions and service connections, or are there any leakage on overflows from storage tanks, which will typically be in the pressure zones, and inside the DMAs, there should typically not be any storage tanks. And then, of course, when we have all these components, and we also have both the amount of revenue water and non-revenue water. So this exercise is really, really important, because if we can do this for each DMA, then we can actually prioritize the right interventions for the right DMAs, the right areas. That means if we have a DMA where we actually need to improve the billing and revenue collection, or do we have a water utility, is the billing and revenue collection the biggest problem? Unauthorized connections, replacements of customer metering. Do we have a very high amount of customer metering errors? Do we under-registrate? Do we not actually meter all the consumption that is used by the customers? Then that could be a bigger problem than the leaks in some systems. And it can also be that in some bigger cities, where part of the cities were built many years ago and some are new areas, that you will have some areas where the customer meters are the problem, other areas it's the leaks that are a problem, and in even other areas that are very old, there may be a lot of unknown connections, which we have to find, and that way to increase the revenue collection. And then, of course, this can also be used to implement pressure management, because when we have such a sectorization of the network, then we can identify which part of the city, which part of the network will have the highest return of investment by implementing pressure management. And then one really, really big warning is that now, when we have such a calculation in place, that sounds easy. We can easily actually calculate the water balance, but the DMA integrity is really, really vital. And by this, I mean that we almost always see that there are a lot of DMAs that are not tight. That means the boundary is not tight. There is some boundary valves that is actually open, maybe more than one, so that whatever flow is running into the inlet chamber to the DMA that we monitor, well, that is actually not equal to what is used in the DMA, because there are some unknown connections that are open, meaning that water is just bypassing the area, or it's being additionally receiving water from another area, and that means our water balance will be more or less worthless. So if we want to go into the DMAs, and also if we want to do pressure management and do pressure optimization for an area, then we need to know that this area is closed on the boundaries, else it will not work. And here's a typical example where we, after a DMA in a bigger city with 100,000 inhabitants were established, this is one of the bigger DMAs, then we must start to monitor the minimum night flow. That is, what was the minimum flow that was running through the meter into the zone every night when the consumption was low. This is a typical, also used as an indicator for leaks. But as you can see, the first days, this was jumping up and down by a huge value. And you even have a few days, or one day here, where the minimum night flow was even, or you have several days where the minimum night flow is negative. This cannot be, of course, so it's not true. So it means that there's something wrong in this DMA. So when you establish a new DMA, it's really good to have some kind of a methodology to actually see that the minimum night flow is more or less stable over a period. If it's not stable, that indicates that there's something wrong with the boundary. Typically, it can also be that there's something wrong with the flow meter, of course, in monitoring the flow into the zone. But at least there's something wrong. In this case, there were more than, because this was a really big DMA, there was more than 10 valves in total on the boundary to other neighboring areas that were where the valves were either leaking or open, where they should have been closed, because there had been some emergency at some point in time where the boundary valves were open to supply the DMA from another location, and then they forgot to close it again after the emergency situation. So this is something that when a system has been operated for tens of years, there will always be a number of valves that are positioned opposite as is planned. And this is especially critical if it's on the boundary of such DMAs or PMAs. And this is also why after, you can see from this plot here, it took a few months. And after this, these valves were rectified. Some were replaced and some were simply just closed. Then the system started to behave stable. And then there are some fluctuations in between where some different operations, but then it was actually after 6 months' time, they started actually to do some leak survey and started to find leaks. This is why you can see that the minimum night flow start to go down in the end of the period here. This is just to indicate that when you have a sectorized network, then to have long-lasting and high-quality valves, this is simply the backbone of a sectorized network. Without that, you cannot use your DMAs for anything because they will be leaking and have false flow in and out of the system, making all your water balance calculations invalid. I put in also here on the right an example from, I think we'll have that in a later session as well. In Copenhagen, they have actually implemented this new device from AVK, which is a positioner, which can actually monitor you can install this on a boundary valve, and then you will actually receive a signal if somebody operates the valve, and then you will get a indication of the valve position if it's open or closed. So you can actually, from the data management who calculates the water balance, you can actually see during which periods a DMA boundary was breached. So you can consider that and take your precautions when you do the water balance. So this is really important. And it's also important to know because if these boundary valves are open and you're doing pressure management, then the pressure management will definitely not work as expected. This is actually then an example of, not from this zone, but another zone in Denmark where we did a pressure management calculation, the potential based on a DMA. And then afterwards there was installed a valve control at the inlet. There was a huge potential for optimization because the pressure at the inlet was normally operating above 56 meters, that's 5 bars. And it was enough to provide somewhere just above 4 bar to ensure enough pressure for all customers inside the DMA. And actually then it was done in 3 steps. The valve at the inlet there was installed a new control valve, as you can see on the left. And then by reducing in 3 steps over time, the pressure was on average reduced by almost 30%. Which actually represents an annual savings of somewhere between 30 and 40,000 euros due to the reduced leakage that would come as a consequence of the reduced pressure and also of the reduced future burst rates. So simply, there are now fewer new bursts in this zone here. And again, this can be done if you have the DMAs, the water balance, you have the measurements at the inlet to every DMA, then you can find the DMAs that has the highest potential for pressure management, and then you can implement the pressure management on individual DMAs, which is much easier than try to do pressure management on all of Copenhagen, for example, which is impossible. You have to do it in zones. Just some example of leaks from around the world. Which doesn't need any fancy DMAs to be detected. We just don't have to. We have to not forget that. Well, use our common sense, and whenever we see something suspicious on the ground, that's a leak, and we don't need any fancy equipment to detect those. The DMAs and the PMAs are designed to find all the leaks that do not surface, and these are the tricky ones to find. Yeah, I think that ends my introduction.
Thank you, Claus. Will you please stay online for questions afterwards? So next would be from Aarhus Water Utility, Flemming Fogh Petersen. Start with introducing to Danish legislation requires that utilities must have a non-revenue water percentage below 10%. So please, floor is yours.
Thanks a lot. And of course, there is some regulation in Denmark that forces us to do something. I'll touch shortly upon it, but mostly I will tell what we actually do because of the regulation we are subject to. My name is Flemming Fogh Petersen. I'm project director in Aarhus Vand. And we are here because we have a long-term partnership with Lviv Water Canal. So we have been present here in Lviv for the last 2 years or so and have a lot of interaction. Actually, I believe it's third time this year I'm here in Lviv. So we do a lot of things together. And since the last year or so, we have been working on non-revenue water reduction, which my colleague Volodymyr will come back to what we actually do here. But it is a big issue here in Ukraine, water loss in the water supply system. Basically, I come from a water utility in Denmark. So we are a municipal-owned water utility in the second largest city of Denmark. And we are here because we have a broader purpose than just serving the consumers of the municipality. Actually, we want to save the world in terms of water, or actually at least do something good and share our knowledge in the world. So we are present in projects in a number of countries around the world, and also here in Ukraine, which is a great pleasure to be here, and also here in Lviv, in this beautiful city. Actually, just a little about why this is an issue on a global scale. Actually, it's very common in countries around the world that you can have water loss of easily up to 50% on the water supply system. And of course, as Claus mentioned in the previous presentation, there's a number of reasons for this water loss. Altogether, if it's physical losses or not accounted for water or anything, we call it non-revenue water, because in the end of the day, it's not paid by the consumer. And I'll just have this map to show what actually is happening around the world. So this on global scale, it's a huge issue. And it's big resources that are lost in water supply systems around the world. And of course, reducing water losses has a number of benefits. For instance, developing new water resources is very costly around the world. So you might not. The first thing is when you have losses of around 50%, the most smart thing to do would be look into reducing those losses before investing in new resources or new water treatment plants or whatever. It's not that it's easy to solve, but it's the right way to do at first. Because that way you can spend less OPEX and less CAPEX in your water supply system. And also energy, because producing water requires energy. So lowering water loss in the system also is lowering your energy consumption. Also, it could be issues of hygiene, in fact, because if you have a very leaking water supply system with maybe even low pressures in parts of the system, there's a big risk of contamination of the water from, for instance, sewage lines. And of course, for the environment, less stress on the environment because you use less resources. Also for the consumers, service levels is increasing if you reduce water loss. In many countries around the world, they cannot have 24/7 supply and one of the reasons is high water losses in the system. So actually consumers, they get very poor service many places around the world. And of course, you need to have better asset management of your system. That's part of it. Public relations. The consumers certainly will like you more as a utility if you are not losing that much water. And again, there could be liability issues and actually legal issues if you have high water losses, and it could also damage, like big bursts will damage buildings and so on. So there is also a legal risk in having big losses. So that's just a few examples. Klaus showed this one in the previous presentation, and I guess having an IWA water balance, as Klaus mentioned, is the backbone of reducing water losses, because you need to fill out these boxes to understand what your problem actually is in terms of the water you lose. And I don't want to comment much more on it because Klaus did that perfect. So I will just go to what we do in our utility. And actually, we have had a history for many years of reducing non-available water. If we go back to 1977, at that time, our production in the city we come from was 25 million cubic meters per year. And if we go up to today, it's around 15 million cubic meters per year. And it's even when we're serving a much larger population than we did 40 years ago. So we have been able to reduce the per capita consumption to, as today, it's around 100 liters per person per day in our utility. And at the same time, also the dark blue line shows the water loss in our system, which have been above 10% back in 1977. And today we are around 5% of total non-available water in our system. Maybe I have more slides, I know. Yes. So when we fill out the boxes in our utility, it looks like this. Even though we are quite a large utility in Denmark, on a world scale, we are not that big. So we produce around a little more than 50 million cubic meters of water every year. And and the water loss, the total water loss in our system is around between 4 to 5%, depending on the year, because we might have more loss in some years than others, because if we have big bursts and unusual incidents happen, but generally it's below 5%. And if we look at this table here, because I know that is also something that applies to the world, main part of the water losses actually is leakage on the service connections. And then that's an issue all over the world, is that when you connect the service line to the main line in the street, there's a risk of water loss. See that every time you do a connection to a main line, it's a risk point where you can risk losing water. So that applies for us, and that applies, I guess, for most utilities around the world. And sorry to say, even though we like technology, there is no really quick fix on reducing water loss in the water supply system. There's many things you need to do, and this figure here just shows that it's not like a technical, easy fix thing you can need to do. It's long-term hard work and priorities in your organization and the finances and all that to do it. Regulation is also part of it. In Denmark, it is so that we receive a fine as utility if we have losses of more than 10%. So, of course, that is a very serious incentive for us to reduce the water loss below 10%. But I'll come a little back to all these bubbles here later. If we go to the regulation in Denmark, I used to say in Denmark we are world champions in taxation. So we have tax on everything in Denmark, and even water is heavily taxed. And of course, if you have high water losses, you also get a fine. So that's how Denmark is. We have a tax on water. We have by law it's mandatory that we have water meters at all consumers. And we also have in Denmark performance benchmarking between larger utilities. That means us as being large municipal utility, we are benchmarked against other utilities around the country in terms of a number of KPIs, and one of them is water loss. So if we are performing poor in terms of reducing water loss in the system, we might be subject to also some more taxation, basically, until we show that we can perform according to the benchmarking. So that is also because water supply is basically a monopoly. Consumers in the water supply, they cannot buy the product anywhere else. So how do you make some kind of competition between water utilities that are basically monopolies. And benchmarking is one of the things you can do, start comparing between different utilities. The timeline on regulation in Denmark was that back in 1980s, there was a tax on water introduced, and there was water meters installed at all consumers. And also there's a law that tells us that we need to test the water meters every 6 years. And of course, all our consumers, they pay by the meter. And then we had this government decision back in 1998 that we are receiving a penalty if we have a water loss of more than 10%. And of course, to fight water loss, you need information and data. So in our case, we have water consumption metered at all consumers. We have DMAs in our network, which means that we have bulk meters showing inflow to certain isolated areas of the system, as mentioned in the previous presentation. We also have real-time data both on the supply side from the water treatment plant and also from these district meter areas. Pipeline registration is important because if you don't have digital pipeline registration, basically you need to start looking into that because it's very hard to work in a structured way with reducing water loss if you don't have any digitalization of all. Burst registration would be a very good thing to have because then you can start tracking the history of leaks and bursts in your system and understanding where are the hotspots in the area, where do you have the most bursts, because it might be that you have pipelines or joinings in that area that fails a lot. So then you can start a more structured way to rehabilitate your system in the places where you have the most incidents. And of course, to do it efficiently, some kind of data storage and data platform to showing what is going on out there is a very good tool to have. Basically, in Denmark, this is how the water supply system looks in most utilities. As mentioned in the previous presentations, we are based on groundwater. I know here in Lviv you're based on groundwater too, but in many parts of Ukraine it's a mix and maybe even only surface water. But in Denmark we are based on groundwater, so we have a number of in our utility a number of treatment plants, and they all pump up the water, treat it very simple, and we have a number of storage tanks in the system, and then we have of course the consumer. And these data is what we need to monitor the performance of the system and to reduce non-revenue water. Yeah, a little about, because the metering side is also something that is a little important. As mentioned, water meters at the consumers, they are mandatory in Denmark. You need to have it. And it's the property of the water utility. So that means it's our meter and it's our responsible to check it and to make sure that it works correctly. And that has been introduced since the 1980s. And we have a system of checking the meters and testing them every 6 to 9 years. And if they fail the test, we usually renew a whole batch of meters that were bought at the same time, because if one in a batch fails, then it's likely that more of them will fail. So we change a whole batch of meter. Yeah, and of course we also have the bulk meters in the DMAs, and we have real-time data from those meters. And in that way, we can monitor, I think, like nighttime consumption. So if consumption certainly rises in an area, that might be because we have a leak or a burst in that area. Something that is also important to fight water loss is what we have of organization to actually have a short response time. Because having big leaks in the system that are running for days and days will certainly increase your water losses. So you need to have some kind of organization in place that can actually respond very quickly to an incident out in the network. We used to say that if we have major bursts in our system, within 2 hours, we should have staff on the site to start doing the work out there. So that is very important that you have an organization in place that can react very, very quickly to any kind of incident that you have out there. And there's a number, in our case, there's a number of departments involved. So it's not like a simple process that is just managed by one person. So you need to have the organization in place in your utility to respond quickly to incidents. Okay. I think for this presentation, maybe the last thing is that you need to have some kind of financial allocation in place to do all these activities, because if you don't have the finances in your utility to have all these systems in place, then that's the place to start to find out how to have the financial allocation. Pipeline replacement is one of the big things that you need to do, and it's very costly to replace pipelines. Both in terms of material, but especially in terms of construction work, and it takes time. So it's good to have a long-term strategy for pipeline replacement. Efficient organization for burst repair is important, and of course you need to have monitoring system in place of some kind. So what you repair is not only based on the reports on big bursts that you see out there, because most of the physical losses they're actually hidden underground. They will never surface. So you need to have some kind of system in place where you can find and repair also the invisible leaks. That's for the next. That's just a cliffhanger. It's for the next panel. Yeah. And the final thing that I think I could mention here in terms of financial allocation is the tariffs that we have in Denmark. Maybe it will be mentioned in other presentations as well, but in Denmark it is so that all operations and investments and reinvestments in the utility is paid by the consumer. So basically the numbers you see here is, for instance, like you can see the total tariff is a little less than 8 euro in our case, and it is combined of a tariff on drinking water, a tariff on wastewater, where people are charged by the cubic meter of used drinking water, and of course we have the tax, and it ends up in a price of these a little less than 8 euros per cubic meter, and I think that number reflects what it actually costs to run a drinking water system in total, including investments and reinvestments and operations and electricity consumption, whatever. It's included. It's included in the tariff. So and I think it's a quite healthy principle, because actually it's the consumers that pays the entire operation of the company, and we know that we have sufficient funds in place to actually do efficient operations. And I think that was my last slide for now. Thank you.
Доброго дня всім. Володимир Білинський, заступник головного інженера Львів Водоканал. Так як у нас більша частина нашої аудиторії українці, то я буду на українській все-таки розказувати нашу презентацію. Декілька слів про співпрацю з муніципалітетом і водоканалом міста Орхус. Отже, ми почали нашу співпрацю у 2023 році. Ця співпраця відбувається на рівні муніципалітетів і також на рівні водоканалів. В Данії в загальному і в загальному по країні в них дуже хороша співпраця між муніципалітетом і водоканалами. Ми також хочемо перейняти цей досвід, покращити наші такі робочі стосунки і, зокрема, в плані співпраці з водоканалом, між водоканалами також. Наша співпраця складається з таких 4 найбільших напрямків. Ми розробляємо стратегію Water Vision 2100. Вона є в місті Орхус вже розроблена, і колеги з водоканалу і з муніципалітету радо діляться своїм досвідом з нами, і ми спільно розробляємо цю стратегію для того, щоб розуміти, куди нам рухатися в плані поводження з водою, в плані поводження з очищенням води, і в кінцевому результаті, що ми будемо мати через, грубо кажучи, 100 років. Також один з наступних напрямків це є робота над очисними спорудами, зокрема над реконструкцією очисних споруд. Ми переймаємо найкращий досвід датський в очистці води. Наші колеги радять нам, які нам кроки робити в плані реконструкції наших очисних споруд. І ми також потрошки, поки що це теоретично, звичайно, тому що є, як завжди, брак фінансування, але принаймні в теоретичній частині ми робимо кроки для того, щоб включити в наш проект по реконструкції очисних споруд, який ми дуже сподіваємося, що буде розроблений, включити весь передовий досвід, який мають наші колеги, який вже втілений в них і який ми надіємося втілити також в нас. Ще один напрямок нашої співпраці, власне, це, що мій колега Флемінг вже розказував, це є зменшення втрат води. Звичайно, ви бачили всі графіки, які Флемінг показував, де в них є дані з 77-го року, і дані щодо того, як зменшувалися втрати. В нас нема такого великого періоду реєстрації наших даних, але ви можете побачити на цьому слайді, ми на Львівводоканалі вже також зробили багато кроків для зменшення втрат води. Починали ми таку велику роботу в 2015 році, і тоді втрати води в нас сягали 56%. Зараз, станом на сьогодні, втрати води в районі 30%. І ми стараємося кожного року зменшувати втрати. І, зокрема, з допомогою наших колег ми почали втілювати проект зонування. Ми вибрали частину міста в Шевченківському районі, де ми створили спільно з нашими колегами 4 зони, які ми зараз спільно опрацьовуємо. В цих зонах ми покроково робили дуже багато речей, і зараз ми сконцентрувалися на одній з зон. Вона є по обсягах водопостачання невеликою, але ми дослідили, що там є серед тих 4 зон найбільші втрати води. Вони зараз сягають в нас там 56%. Це є, ми її називаємо зелена зона. Це є здебільшого зона, яка складається з індивідуальної забудови, одно-двоповерхової. І коли ми під час роботи з нашими колегами встановили на вході в цю зону лічильник з реєстрацією даних, ми побачили, що також нічне споживання є досить високим для такої індивідуальної забудови. Зараз ми на основі цієї зони хочемо розробити такий пілотний проект, де ми хочемо втілити всі речі, які вже наші датські колеги пройшли. Зокрема, це є і заміна мереж, і встановлення індивідуального обліку на врізці в кожну будівлю, а не всередині в будівлях, як зараз є. І також перепідключення всіх споживачів до нових мереж. Ми дуже сподіваємося, що ця робота буде зроблена в найближчий рік. Ми плануємо її виконати. І ми плануємо, що завдяки цьому втрати води в цій зоні знизяться принаймні до 10% з 56%. Це мав би бути такий пілотний проект розроблений, який би показав, що ці всі кроки, які ми робимо, вони є правильні. І на прикладі цієї зони ми будемо продовжувати нашу роботу по всьому місту для того, щоб в кінцевому результаті зменшити наші загальні втрати води до, ну, звичайно, що ми не зможемо зразу там до 5%, як в Орхусі, але ми будемо до того рухатися. Отже, які переваги роботи в загальному по зонуванню, так, по цій роботі, якій ми спільно займаємося? Ну, в загальному це тільки переваги, тобто мінусів немає в цій роботі. Зокрема, це є, ми побачили, що коли ми концентруємося над роботою над однією зоною, в нас є детальний аналіз водопроводів, які там проходять, перетинів водопроводів з каналізаційною мережею, потенційних точок, можливих скритих витоків. Це є повний аналіз нашої мережі. Також ми робимо покроковий план, як зменшувати втрати покроково. Тобто, наприклад, в нашому випадку ми встановили засувку посередині зони для того, щоб зрозуміти, чи в нас втрати є в верхній частині зони, чи в нижній частині зони. Ми робимо такі експерименти для того, щоб зрозуміти, де ці втрати, для того, щоб їх можна було локалізувати, для того, щоб їх можна було зменшувати. Також завдяки тому, що ми встановили цей лічильник на вході в зону з онлайн-моніторингом, ми можемо бачити нічне споживання і ми можемо швидко реагувати на будь-які аномалії, які ми бачимо. Якщо, наприклад, нічне споживання підросло, ми розуміємо, що в цій зоні з'явився витік, ми реагуємо, ми туди скеровуємо нашу аварійну бригаду, яка знаходить, яка ліквідовує, і таким чином це також зменшує наші втрати води. Робота щодо тиску. Також ми побачили, ми встановили на вході в зону датчик тиску, поки що не регулятор, а датчик тиску. Ми побачили, що тиск є зараз занадто великий для цієї зони, для малоповерхової забудови. І в планах є встановлення регулятора тиску. На попередній презентації ви бачили, що колеги з Данії таким чином зменшують тиск на 26%. В нашому випадку ми проаналізували разом з нашими датськими колегами, що це може бути зроблено в 2 рази. Тобто це не є 26%, це є 100%, так? І таким чином, зменшуючи тиск, ми також зменшимо потенційні скриті витоки, потенційні якісь аварійні ситуації. Таким чином також буде зменшено втрати води. Також це дозволяє нам робити планування і планування наших інвестицій в цю зону, планування, що нам потрібно зробити, що інвестувати, що спочатку зробити, що потім, для того, щоб також ця робота була ефективною. Ну і, звичайно, я би мав поставити цей пункт першим в цьому переліку. Це є цей досвід, який ми отримуємо, коли працюємо разом з нашими датськими колегами. І цей досвід є неоціненний. Це є щоденна робота. В нас є, крім нашої внутрішньої роботи, в нас є щотижневі онлайн-зустрічі з нашими колегами, де ми разом думаємо, що робити далі, як робити. І завдяки цим всім порадам ми маємо хороші результати, і ми надіємося на подальшу нашу плідну співпрацю. Тому ще раз хочу щиро подякувати нашим друзям з Данії, які підтримують нас завжди, які радо приїжджають. Ми завжди тішимося вашим приїздом, і ми дуже щасливі, що ми маємо таку співпрацю з вами, і надіємося, що вона буде довготривалою. Дякую.
So now we are open for questions, both for Klaus online, Flemming and Volodymyr. So please come forward with your questions.
Дивіться, в мене є два основних питання стосовно наших датських колег, де вони розказували про облік і локалізацію обліку по районах. Перший, як ви робите облік закульцованих систем? Коли тупикова гілка, то все зрозуміло. У нас є один лічильник. Коли вона в нас закульцовується, яким методом ми будемо прораховувати ці питання? І в подальшому, якщо закульцована система буде збільшуватися, від неї буде далі відгалуження йти. І друге питання, як працює саме виявлення витоків? Чи це якась безперервна нитка, яка обриває сигнал при пориві, чи це якісь датчики вологості ґрунту? Це є поки що два, якщо буде ще час, лише добавлю. Дякую.
Klaus, the question about the loop system, I think that's something for a consultant.
Just in general?
How do you do sections in a loop system, right?
Yeah, when you do sectioning, and of course I couldn't get into all these details in the presentation, but two very, very important tools when we do a sectioning plan is to have some good GIS data, which Fleming also mentioned in his presentation, is important for knowing your network. And then we create also a hydraulic model using the GIS data. That means we will have a hydraulic model that contains all the loops, all the clients, all the customers in it with demands and everything. And then we can actually calculate, we can find the areas, we can use some topological tools to group customers of different same types into some clusters. We can use the main roads as natural boundaries to DMAs. And then when we start by work our way into where could the DMAs be located, then we have to look at all the loops that will then be on the boundary of the DMAs in the beginning. And then we can try to find out, using the hydraulic models to do hydraulic simulation, to find out which of these loops can actually be removed. Can we simply cut the pipes, or can we put a closed valve on the pipe? If it's on the boundary to the DMA, then we would typically, if there's a lot of loops that are on the boundary of the DMA, we will find out if we have to upgrade the inlet to the DMA so we can provide enough flow. And then we can be able to cut these loops. And if there's a lot of loops, we would recommend that some of them are cut and maybe one or two of them are converted into an emergency inlet. And that is the basic of it. And then if we have big DMAs where you can have other kinds of problems inside the DMAs, we will probably also, that will typically be part of a rehabilitation plan. But we would typically also try to remove some of the loops inside the DMAs, or at least have them closed in daily operation if it doesn't cause any pressure problems, because loops are not very convenient when we are talking water quality, because they increase the risk of having stagnation in the water and old water in the system. I hope that answers the question.
Yeah, and maybe I can reply on what we do in terms of how we detect leaks in the system. Because when we have constructed these DMAs, we have just maybe one or two inlet to a certain area of the city. And we have online data on the water flow in those areas. And normally we look at the nighttime consumption in the area, because nighttime consumption in most areas, or at least you know the consumption pattern, the normal consumption pattern, but nighttime consumption should go down between 2 and 3 at nighttime to the same low level, because you can, at least in normal household, you will expect very low consumption at that time. And basically that is how we detect the hidden leaks, because the visible leaks are often reported by people that see them, but and we react immediately on that one. But the invisible leaks we detect by in the DMAs by the nighttime consumption, and when we identify that it increases at nighttime, then we go out and do leakage detection by different methods that we have. And actually, I have a laser presentation. I will show you something about what we do when we do identification of the hidden leaks. But it's I think it's the same all around the world. You need to find out where the flow in the network is, and the main part of it is by acoustic methods. So you can listen to the valves, and you can find out, okay, there's a flow in this area that should not be there. So that is one of the primary tools that we use.
We will continue at 2:00. Now we have defined, let's say we have all defined our DMAs, our district area, metered areas.
Хотіли запитати, як часто в Данії переглядають тарифи і хто є регулятором?
Actually, we have two levels of approval of tariffs in Denmark. We have one at the national level, that is the benchmarking system, for instance, where utilities are benchmarked against each other. That's something that happens at national level, and that can affect the tariffs because we might be subject to be more efficient if we're not performing compared to other large utilities. But the tariff in general is approved by the municipality. So every year we need to send in a tariff sheet and some accounts that shows that the tariffs that we charge actually can be shown in our accounts. So it's approved by the municipality. Basically, that is the end approval, so to say. Even though there is a national part of it too. But every year there are regulated tariffs. Yeah.
Запитання, яке програмне забезпечення використовуєте під час гізмоделювання систем водопостачання, водовідведення і гідравлічні розрахунки самої системи?
I guess it could be like any kind of system, because in our case we use MapInfo and ArcGIS is widely applied also. QGIS, which is free, is also very useful. I think it's not so much depending on the system. It's more depending on the data that you have. So basically, it could be any kind of GIS system.
Цікавить наступне питання. Хто є власником мереж водопостачання, водовідведення в Данії, і чи є приватні установи, які володіють мережами?
In Denmark, the entire assets in a water utility, that includes both the drinking water supply system and the wastewater system, in our case, it's our ownership. So we have huge assets and it's entirely owned by a utility in the case of Denmark. We don't have any big global private operators in Denmark to operating the water supply system so far, and I don't think it's going to happen either. Oh yeah, and then we have a big number of very small waterworks scattered around the country in the villages, and they are generally owned by the consumers in the village. So we have a big number of those also.
Тобто при будівництві мереж все передається водоканалу. От, до прикладу, якщо я, як фізична особа, потребую підключення до послуги водопостачання, прокладаю певну кількість там кілометрів, погонних метрів водогону. Це виступає як моя власність, а не власність водоканалу. В Данії це автоматично врегульоване питання, передається автоматично на баланс надавачу послуг.
The part in terms of connection, you need to pay a connection fee. So everything that is outside private property is ownership of the utility. But if it's a network inside private property, it's the ownership of the private owner, so to say. But our responsibility ends at the boundary of the private property and ownership also. Yes. Yeah, and the connection fee depends on the size of the connection. So if it's a big developer developing an area, they need to pay accordingly to the size of that connection they have. Basically, and the metering, that's another question, because it might be so that we just charge the meter to the entire big property, but in most cases we charge by the consumer end still, because someone needs to find out how it's distributed between the consumers inside the property, and we have the backbone system to do that. So normally they will ask Aarhus to do it anyway, even though it's inside their property.
That was panel number 2. Now we say we have defined our network. We have divided into sections. Now in panel 3, which is will be starting at 2 o'clock after lunch. Then we go deeper into, okay, then how to find the leaks. What measurements do we have to reduce non-revenue water, and what measurements do we have to find the leaks? So that will be next panel at 2 o'clock. So thank you for now. So we will start now. As I said before lunch break, we have now we have defined our DMAs. We have sectionized our distribution network. Now it's a question about finding the leaks and how to reduce the volume of lost water. So here we have Nikki. Where are you? There. Yep. So we have Nikki from Danish Water Innovation. We have myself from AVK. I will talk about pressure management. And we have Alexei from Grundfos. And I guess we will talk a little bit about the same pressure management, but valves or pumps. Okay, so let's get started with Nikki and how to find the leaks.
Hello, everyone. My name is Nikki Jørgensen, and I have a company that finds leaks on an everyday basis. We do that for the water utility companies, but also for private households. We are always on the road 24/7. And we help, we have about 2,600 water utility companies in Denmark. So many of these only have 1 to 3 employees, and they don't have the capacity to solve their own issues when it happens. So that's where we come with a truck full of methods. Every leak is different, and we use multiple methods in finding these leaks. So on an everyday basis, we know what works in what situations. Of course, when a leak happens, the first thing that we typically experience is the water utility company has made some pressure management during the nighttime. They can see there's a fall in pressure. And this is when people are typically asleep. So following a pattern during the nighttime is a key indicator for them that they have some non-revenue water. Now, non-revenue water for us is water that does not go through the meter and that is not paid for is non-revenue water. And in Denmark, when you exceed 10%, then it starts costing for the water utility company. This is a very good thing to place because this motivates the water utility companies to actually try and find these leaks and not just heighten the pressure, wasting water, wasting energy, and creating a lot of water somewhere that they don't quite know where. So typically, when we come out, we have some instruments that we use to find these leaks. We have a listening stick that we use on all the valves. Here we typically go from valve to valve, and then we listen to this unique sound that a high water pressure system makes when you have a hole and it comes out. Now, different materials are being used, so you have a different sound on all these different materials. This takes time in training the ear, and you also need relatively peace and quiet around you. If you have heavy traffic, if you have airplanes, if you have trains, people walking the dog and whistling, all this sound is basically in the way. So it takes time to train the ear in finding these sounds. Once we have heard a unique indication of leak, then we will typically use a correlator. A correlator is 2 devices you put with a distance on plastic, typically under 300 meters. preferably 70 to 110 meters. And if it's more like cast iron or a more harder material, then we can reach the full 350 meters. And then this device actually communicates with each other, listening to the sound, and then it will show the distance of where this leak has arrived. If we cannot find it with a correlator, we could use tracer gas. Tracer gas is accepted using in drinking water. It's actually just an air that you can detect. And typically we fill it into the pipes where we can close off in both ends where we believe the leak is. And then above ground, we have a vacuum that will make a big noise when the gas comes out. We also use that a lot in the private households because it's very hard to find these leaks in private households, especially with water running through for water floor heating, because they typically have concrete or floors or some kind of hard material. But the gas will always find its way. All these methods that we use, it's a lot of manual work. And as I told you, we need peace and quiet to kind of listen. Now, after the war in Ukraine, the energy prices in Denmark went up 1,400%. And that changed our everyday because we used the nighttime to go around and listen. And now with the energy prices so high, people put their washing machines, their dishwashing, all these machines are running at night when the energy price is at its lowest. So we heard more noise than we've ever heard before, complicating our work in finding these leaks. So what do you do in that kind of situation? You need a tool to be able to filter this sound away. You have loggers that you can put in your net, but it costs quite a lot to put this hardware all over your net. So we started looking into AI and machine learning. With AI and machine learning, you can have all the noise in the world. And even with this noise, it is able to sort out this noise and still be very indicative of the leak sound. It can multi-filter in a second, and then it can allocate these sounds. And we have a pilot project running in Denmark right now with 2 water utility companies. And we've been able to locate leaks with 97.6% accuracy with the use of also putting hydrophone technology into the water track. The hydrophones, they reach 1 kilometer. So you have a very large reach. And because of this hydrophone technology and the incorporation of other data sources from the pressure management system, from the household meters of actual consumption, it can also be from sectional meters, meaning what water goes into this section and what amount of water is actually going through the meter. So all these data sources make this machine learning module very, very intelligent. So with the use of this kind of technology, you are now making all this manual work into automative work. You still need to localize the leaks. 97.6%, it's good. You get across, it should be here. But then you still go out with the microphone and you listen. Because in Denmark, the water utility companies, once we have marked here is a leak, they will only dig 2 times 2 meters. So we have to be very sure that it's at that point. Digging is expensive. Digging is not very nice for the citizens living in the area. And having to reestablish is also expensive. And then there's the work pay. So they give us 2 times 2 meters. And the worst thing that can happen for us is that they dig down and they find a dry hole. Then we have a really, really bad day. So it's very important to be able to understand. One thing is the manual work. That's where you should start. It's always effective listening point by point and being able to use the instruments that we use today. But also being able to go over and make yourself ready for the digitalization aspect. When we started integrating all these different datas from different companies, trying to create a higher intelligence, we found out that all the data, it needs the same timestamp. If it doesn't have the same timestamp, you can't use this intelligence. Also, we have these blockages with when you start taking data through an API, then it will automatically time out after 3 hours. Why? Why shouldn't you be able? Well, because it costs a lot of money to take data. So we call it API readiness. It is actually getting people ready to accumulate all the data and getting it ready to actually be used in a more automated way. This is not time consuming if you do it from the beginning, but it's very important that you don't think, oh, I have a lot of data, now we can get some intelligence. No, you need to have a precise plan on how you will use this data from the beginning so that you can actually get this extra muscle in the machine learning way. For Ukraine, it's very exciting for us to see that there's so much difference between all the water utility companies. And that's why it's very important to meet the Ukrainian water utility company in the place where they have started their journey. Is it manual work where they have to go around with the listening stick? Is it a logger that they have money to be able to place around and make a strategic where you split up your whole area in, let's say, 12 sections, then you can put loggers in one section for 1 month. It will find all the problems. Then you move it to another section, move it. So you have a strategy for this that gives you a better circular economy. And then also, do you have a local partner that can help you leakage detect with all these different methods? It's very much the instruments doing the job, but you just need to know how. And that's very simple because we teach all these people to do proactive leakage detection. And I usually say that men and manuals don't go hand in hand. So by actually showing and demonstrating how these tools work, that is the best knowledge of how to use it and be proactive leakage detector. I find it a very nice job because we're on the hunt every day. In Denmark, we have an average of 7% wasted water, drinking water. So it's getting harder and harder to find. But still, our company finds about 3 leaks every day in average. So yes, some of them can be from households. Those are minor leaks. But we also find a lot of leaks in the water utility companies. And our neighbor country, Sweden, they have about 35% water waste, non-revenue water. So coming over there, we find the leaks very quickly, and then, the hunt is not as exciting. But again, we're always available to be able to help the Ukrainian people in taking the lowest fruit. Where will your journey start? And we will share all our knowledge with you in order to find these leaks. So basically here you see the different, this is the ground microphone that we use, where we go step by knowing where the water pipe is. And this is just like one big ear. So this is how we can get the final indication of here is the leak. This is the correlator where you have 2 points. And between these 2 points, they will start communicating when you've placed them on the water pipe, and it will show you where the leak is within that area. And this is the more automatic version where you just place a lot of loggers and they will correlate constantly and monitor your network. And then they will show where these leaks are. But still, after you have found this method or you find the leaks with this method, you still have to use this big ear in order to be able to put the final X. Do I point here? So here are typically sounds we hear when we go around. As I told you, cars, planes, trains, we also hear birds. If you have a bird singing in the tree, it's just in the way. It sounds nice, but you need to be able to filter these sounds away. People walking their dogs, they whistle a lot. It's very annoying when you're trying to find a leak. There could be a service guy banging on all the pipes in a building next door, or you can have washing machines or running toilets. We hear everything with the use of the ground microphone. So I just need to see it. This is a good sound. This is no leak. This is water being consumed inside the water pipe. This is what we like to hear. So this is a washing machine that is running. We hear everything in this water because sound travels so well inside the water field. Now here is a leak on cast iron. The more harder the material, the longer the sound will travel. In plastics, you have a shorter distance. So this is a clear indication of cast iron leak. And this is where we become very happy as leakage detectors. Copper, it's a terrible sound, but a very unique sound. So we don't have many copper pipes in Denmark, but this is to show you how different the leakage sounds are. PVC is the most common that we have in Denmark at the moment. Also very indicative. Now this is a very big leak that we got the sound file from. And here we had about 600 to 800 liters of water coming out in about half an hour to 45 minutes. And what had happened was actually that these people with the fiber optics for the high-speed internet, they had shot it through the ground directly into the pipe, and the pipe had basically exploded. Here we have the steel leak sound. And when we go around and leakage detect, you don't have one area with just one material. You might have a mix of materials. You might have the old material that has been there for many, many years. And then you've had a leak, but then you place PVC when you repair. So it goes from like steel to PVC to steel. So you constantly are with different materials. And that's why either you have a very trained ear or you start using the technology that can filter out these things in order to find the leakage. This is an old water meter. Very annoying sound, because how can you hear the leaks when something like this is going on? So these are the types of things that we experience on a daily basis. This is an old water meter. Oh. And then we have the bird. Can you start it again? So that was the bird sound. And we use these files to train people because they think they think every sound that they hear is a leak, and it's just not. and digging holes where it's dry is very expensive. So, so with AI and machine learning, once you have all these audio files of something indicative, then the machine learning modules are clever enough to be able to filter these in different variations. And then you will get a much, much better result. So because of what we've done until now, where we have an average of 7% in non-revenue water, and we have the data sources available, we can now proceed our journey into becoming more digital and more automated processes in finding these leaks. So yeah, that was all from me.
So that was one way of reducing the lost water. Another way to do it is, and you have heard it several times this morning, pressure management. Pressure management should be used for two purposes. One, reduce the volume of lost water, and secondly, extend the lifetime of your pipe network. It's proven, some professors has proven that there's a correlation between the pressure and the amount of lost water. The higher the pressure, the more water you will press out through leaks and cracks and bursts and so on. So a rule of thumb is if you lower your pressure with 30%, you will also reduce your lost water volume with 30%. As I said here, these professors has made some calculations that 38% pressure reduction will also extend the lifetime of your pipe network because it will lower the burst frequency with 50%, 53%. And this is the graph they did. They examined 200 different water utilities. And here you can see that around 38% will give you a lifetime, a reduction of pipe burst of about 53%. So there's all reason to manage the pressure in order to lower the water loss and extend pipeline life. So I will give you an example from, of course, Denmark. It's a minor utility. It's not that big, but his challenge was that all his distribution network was placed on a hill slope. So from the upper point, there was 42 meters above sea level, and in the lower part, it was only 2 meters above sea level. So you can imagine the water column from 40 meters to almost zero will give you an extra 4 bar pressure. So up in the upper part, which is here in the lower section of the photo or the image, here the waterworks, the pumping station will pump out the water with 2.5 bar. That's the normal service pressure in Denmark. And if then something happens, all the pressure from above will go to below, adding 4 bar, meaning 6.5 bar in the bottom, which his pipe network couldn't stand. So what we did was that we divided the total network into, and now it's not called DMAs anymore, now it's called pressure zones. So we divided the network into 4 pressure zones. We closed the border around the zone, closed all the valves or cut the pipes, and we established one entrance, an inlet chamber for each of these pressure zones. And here you see the inlet chamber from outside. It's a simple manhole, and inside you will have this arrangement. You will have a pressure reduction valve, a water meter, and a strainer, because it's a sensitive arrangement here that requires totally clean water, no sand, no small gravel or particles in the water that were stuck into these small pipes. So this is inside, and here you see on the side, there's a control box that will control the valve, and I will come back to that. So what it is that we're doing is, of course, a normal pressure reduction valve. You set the downstream pressure at a certain point, and then because of consumption in the pressure zone, then the pressure will also go up and down, up and down. So if you have high flow, the pressure will go down. If you have a low flow, pressure will go up. And what happens? You will simply motion your pipe network up and down, and all of a sudden it breaks. So that's also why you should introduce, as I said before, pressure management in order to straighten out these curves here. So it's a question about turning it around so that we have constant equal pressure in the zone, and then the valve will then regulate according to the flow, and by that keep the pressure stable in the zone. This is how it looked when we first started. As you can see here, the pumping pressure from the waterworks, and here the pressure in one of the zones. And you can see here it's the same, up and down, up and down. And then one afternoon at 3 o'clock, he pushed the button and then start to equalize the pressure. And you see the blue line is still the pumping pressure outside the zone. So that goes up and down, up and down. But inside the pressure zone, it's quite stable. It's only fluctuating with 0.2 meters water column. And here you see another very interesting example. The pumping pressure, the pressure in the zone, and here the flow. And what we realized all of a sudden was, you also heard about nighttime flow, that in the middle of the night from about 1 o'clock in the middle of the night and until say 5 o'clock, 5:30, it's this nighttime flow. And then in the morning, people are getting up, take a shower, cook the coffee, and then the flow will raise again. But the good thing about all it was that sometimes you see here, it hits the zero curve. So no flow at all in these intervals here, meaning no leakages in this area. Because if there would be a leakage, then you will never ever hit the zero line of flow, because there will constantly be a flow. And that's also a measure how to compare, yes, thank you. Compare pressure zone to pressure zone. What is the flow? How many people are living in there? And this nighttime flow. Here we have zero. In other places we don't hit the zero line, and then we start looking for leakages in that area with listening sticks or noise loggers or what have you. So how does it work? You have flow data from the flow meter. You have a pressure data. And then in the box, that will control whether to lower the pressure or higher the pressure according to the flow. And that's how you get this stable line in the pressure zone. So the flow will indicate higher flow, as I said before, will lower the pressure. Then we have to turn up the control valve, and low flow will rise the pressure, and then we have to turn down the control valve. So that's how it works in reality. You see here also, I actually mistaken. This is the pressure sensor that goes into the control system. This is only a kind of a guarantee that if all of a sudden the flow exceeds typically a leak or pipe burst, then the upstream pressure gauge will indicate that either we have a situation in the zone or we don't have, the pump has stopped, or so they don't go and look for leakages, go and see what's happening with the pump. So it's kind of a safety precaution. And then after that, then instead of having the pressure sensor next or downstream side of the control valve, then you move the pressure sensor into your zone, because you have something called a critical point in your zone. Could be a hospital that always require water, could be a water-consuming industry, it could be a high-rise building where you have to guarantee a certain pressure or a certain volume of water, called a critical pressure. Then that pressure sensor will then control the control valve instead of next or downstream side of the control valve. Yeah, and then next step is, of course, to have it communication via the cloud. So instead of having it wired or close together, then you send all the information in the cloud and then back into the control system or into your SCADA system. Yeah. Another advantage here, we also had another project where the pressure was actually too high and people were getting used to have this high pressure. And then they simply said, now we have to reduce the pressure. So they, in one go, went from, let's say, 4 bar to 2.5 bar. And immediately people started complaining, hey, there's no water coming out of my tap. There was water, but it was not with that kind of speed that they were used to. So by this system, you also can lower your pressure slowly over a period of time. Nobody will notice it, and you will have no complaints. So that's another way also to save water. You heard this morning that we have a water consumption of 100 liters per person per day. If you want to reduce, I don't know how much you are using of water here, but if you want to save water, you can also lower the pressure slowly with no complaints afterwards. So that's another a way to save water. Yep, thank you.
First of all, I would like, from my side, I'm sure everybody will join me to say thank you very much for Danish people, first of all, for your constant support of Ukrainians, and also for Danish specialists who, during this really difficult time for Ukraine, you come here and you try to share your experience, your knowledge with us, to teach us and to make us better and to help us. So we really appreciate. Big thanks from all of us. Thank you very much. Я думаю, я українською мовою продовжу, тому можна відпочити трошки від навушників. Всім доброго дня. Мене звати Андріященко Олексій, компанія Grundfos Україна. Це дочірня компанія датської компанії Grundfos, тому я тут, бо датська компанія. Багато хто з вас, верніше, знає, я думаю, нас як виробника насосного обладнання, сподіваюсь. Деякі з вас знають нашу компанію як виробника рішень для дозування, дезінфекції, обробки питної води. Але сьогодні в нашій панелі ми говоримо про втрати води, як зменшити втрати, і ви вже почули, очевидно, щоб зменшити втрати, нам треба їх, наприклад, знайти і замінити мережі, або зробити наші мережі краще. Нам розповіли, як можна шукати витоки води. Також Майкл нам розповів, як можна зменшити втрати за рахунок стабілізації тиску або зменшення надмірного тиску, зменшення коливань тиску. Якраз коли у нас йдуть зміни в системі або надлишковий тиск, теж ми маємо втрати. Якщо ми з цим це питання вирішимо, ми можемо зменшити втрати води. Але якщо ми задамо питання, що створює той тиск надлишковий в системі або коливання тиску, очевидно, це насосна станція. Тобто у нас є насос, він працює, або група насосів, є надлишковий тиск. І от я би хотів поділитися з вами досвідом, як за допомогою рішень компанії Grundfos можна керувати тиском, саме керувати насосною станцією, і тим самим, як наслідок зменшити теж витоки води, зменшити споживання електроенергії. От поговоримо трошки про це сьогодні. Ну, ви бачите такий графік, прокоментую його. Це такий стандартний профіль будь-якої системи водопостачання, можна так сказати. Ви бачите, зліва всі спимо вночі, як правило. Далі ми прокидаємось, у нас збільшується водопостачання, ми всі там готуємо їсти, потім ми йдемо на роботу, воно спадає, і вечором ми приходимо додому, знову в нас є підйом водопостачання, далі знову спад. Ну, зазвичай, як насосна станція покриває такий профіль. У нас може бути якийсь великий насос або група насосів, ми можемо там, як раніше, або і зараз деякі так роблять, десь там дроселювати ці насоси, або там засувку відкривати, закривати. Ну, це такий не найкращий спосіб. Далі ми навчилися використовувати частотні перетворювачі, ми використовуємо, наприклад, каскадну схему, коли у нас вночі працює один насос, а в день в час пік працює 5. Можемо додати частотні перетворювачі, тоді ще керувати обертами насосу і, відповідно, покривати піки або просідання вночі. Ну, ось зазвичай ми так працюємо, на більш-менш сучасних станціях. І, як правило, ми контролюємо тиск на виході насосної станції. Але якщо ми подивимось, що відбувається в системі, я трошки зараз вперед перемикну. Якщо ми подивимось, що відбувається в системі, то впродовж дня міняється витрата, і відповідно у споживача, саме там, де критична, де у наша мережа, споживач, у нас тиск весь день він плаває, тобто він виростає, падає. І от якраз Grundfos подумав, як ми можемо цьому запобігти або вирішити цю питання. І на цій схемі показана типова насосна станція і показані такі от споживачі умовні. І ми пропонуємо систему, яка складається з таких основних елементів. Це датчики тиску, які ставляться максимально близько до споживача. Ці датчики тиску передають інформацію про тиск на насосну станцію. Насосна станція з розумним контролером будує модель цієї системи, вивчає її, і після певного періоду навчання, я покажу скільки, насосна станція працює таким чином, що вона контролює тиск не на виході насосної станції, не отут, як це відбувається зазвичай, а вона працює так, щоб у нас стабільний тиск був саме отут, у споживача, щоб при зміні витрати у нас тиск не мінявся. Якщо ми, наприклад, встановили, що ми хочемо тут мати там 3 атмосфери, 3,3, наприклад, або там, різні варіанти є, то від зміни витрати наша насосна станція завдяки контролеру буде керуватися так, що цілодобово тут буде триматися 3 атмосфери. Відповідно, в цих ділянках мережі, в цих ділянках сіреньких, у нас не буде коливання тиску. Давайте подивимось, чи можливо це на графіках. Тобто я вже сказав, витрата змінюється, ви бачите графіки, час, у нас вночі йде просідання витрати, є пікові якісь моменти витрати, і відповідно, якщо ми використовуємо систему DDD, це у Grundfos називається DDD, розшифрувати це можна як витрата за потребою, тобто за потребою. Ви бачите, проходить період навчання системи, і потім ми бачимо, що тиск на виході насосної станції, це саме тиск на виході насосної станції, він коливається, але що буде при цьому у споживача, от ближче до споживача, зараз вибачаюсь. Після періоду навчання цієї системи у споживача тиск буде стабільний. Тобто, ще раз, витрата в нас міняється, на виході насосної станції тиск у нас коливається, бо система вивчила, як міняється наша витрата. У споживача витрата стабільна. Відповідно, в більшій ділянці мережі у нас тиск не буде коливатися зі зміною витрати. Тобто це вже результат роботи системи. Якщо ми подивимось на, як скажемо, порахуємо площу, можна так сказати, от між кривою і прямою, то фактично це все наша економія електроенергії. Тобто крім захисту нашої мережі від надмірного тиску, крім коливань тиску і можливих поривів, ми ще, використовуючи такий алгоритм керування, ми ще досягаємо суттєвої економії електроенергії. Ну, знову, да, схожі графіки ще раз. Тобто це як коливається тиск у споживача без застосування системи контролю DDD, про яку я зараз розповідаю. Тут ми цю систему поставили, її запустили, бачимо, відбувся період навчання, коли система зрозуміла, як працює система, як працює споживач, вона побудувала модель, далі ми отримуємо стабільний тиск у споживача. Споживач – це, я називаю це, там може бути мікрорайон міста, наприклад, або якийсь, або навіть якесь там селище, тобто це може бути від маленького до великого. Так ви бачите на екрані, хочеться відмітити, що цю систему Grundfos почав впроваджувати десь 7-8 років назад. По світу ми маємо вже там 300 плюс інсталяцій. Дуже багато таких систем запущено в Польщі. От поляки, вони взагалі побачили в цьому перевагу. І питання, чи є це в Україні. То вже в цьому році ми реалізували 3 проєкти в Житомирі. Вже є перший досвід. Ви бачите, насосна станція Grundfos була поставлена, насоси з частотними перетворювачами. І так виглядає дистанційний датчик, який ставиться максимально близько до споживача, тобто десь в критичній точці, саме там, де ми хочемо мати стабільний тиск. Цей датчик безпровідний, як я сказав, сім-карта, акумулятор, який розрахований на 10 років роботи. І, відповідно, він міряє тиск, накопичує дані, передає безпровідним шляхом на контролер. Відповідно, контролер, який знаходиться біля насосної станції, між ними відстань може бути і десятки кілометрів, неважливо. Цей контролер, він накопичує дані, в ньому є певний алгоритм, і він керує цією насосною станцією за алгоритмом, плюс за даними, отриманими з того датчика. Ось ви бачите, це насосна станція Вітрука, наприклад, в Житомирі. Після заміни насосів і після впровадження методу такого керування ми досягли економії електроенергії 51%. Тут можна, наш такий розрахунок показує, що сама заміна насосів дала приблизно 30-35% економії, а от впровадження системи контролю тиска – це приблизно 15% економії. Але крім економії, я нагадаю, ми говоримо про витоки води. Порахувати, наскільки тут зменшились витоки після впровадження, наскільки ми стали мати менше аварійних ситуацій в мережі, в мене цих даних, на жаль, поки що нема, можливо, водоканал пізніше поділиться, але очевидно, маючи стабільний тиск і не маючи коливань, не маючи надмірного тиску, явно мережа у нас страждать буде набагато менше. І ви бачите, питома норма, вже я перегорнув, зменшилась теж в 2 рази, відповідно, з 360 Вт на метр кубічний перекачаної води до 170 приблизно. Теж графік з цієї станції, ви бачите, ось період навчання, от у нас там всі показники пригали. Блакитне – це наша витрата, яка міняється протягом дня. І ось ви бачите, коли система пройшла навчання, от у нас такою помаранчевою лінією стабільний тиск. Тобто це саме тиск у споживача. Тобто витрата міняється, тиск насосної станції червоним на виході з насосної станції міняється, але тиск у споживача стабільний. Хто з вас уважний і добре бачить, може звернути увагу, що ось тут, наприклад, наша помаранчева лінія почала отак просідати, і задати питання, що сталося. В цьому випадку наш клієнт, Житомирводоканал, вони вирішили до системи DDD ще додати регулювання тиском за часом. Тобто вони поверх працюючої системи, вони ще сказали, що я в контрольній точці хочу в час пік мати, наприклад, 3 атмосфери, а вночі мені там достатньо 2 атмосфери. І ось ми нічні режими, коли у нас майже немає витрати, бачите, люди сплять. Ми ще і вони захотіли, щоб в цей час наш тиск був ще нижчим. Ну, я не можу сказати чому, але чомусь вони якби для себе так вирішили, бо вони знають свою систему, можливо, знають потреби там того мікрорайону міста, і вони вночі взагалі зменшують тиск. А нижчий тиск вночі – це ще додаткова економія. Коротко, з чого складається система? В нас є насосна станція, обов'язково мають бути однакові насоси. В нас є частотні перетворювачі, обов'язково для кожного насосу. Без цього це не працює. В нас є контролер, який отримує дані вхідний тиск на насосну станцію, вихідний тиск і обов'язкова витрата. Тобто в нас має стояти поруч витратомір. Далі в нас є модуль з сім-картою, який отримує дані з безпровідних датчиків. В нас є датчики від 1 до 10, може бути на одну систему. Як правило, досвід показує, що достатньо 2, але можна більше. І відповідно датчики накопичують дані, передають безпровідно на насосну станцію, і вже контролер накопичує ці дані і відповідно управляє насосами. Які ми ще перевагу отримуємо? Наприклад, в системі все ж таки відбувся порив. То система побачить, що витрата в якийсь період стала більше, ніж вона була статистична. Да? Тобто, наприклад, вночі у нас завжди витрата була там 40 кубів, і система це реєструвала раз, і приходить якась ніч, і у нас витрата там 70 кубів виросла. Да? То система про це просигналізує, вона покаже, що ваша витрата різко зросла, тому водоканал має оцінити, що відбулося. Якщо він там, наприклад, підключив якийсь новий будинок, то водоканал розуміє, окей, у нас з'явився споживач, значить витрата виросла планово, якби заплановано. Да? Якщо, наприклад, ми нічого не міняли в системі і раптом зросла витрата, то система покаже це, і водоканал зрозуміє, що, напевно, відбуваються якісь екстра витоки, тобто відбулася якась аварія, тому що витрата зросла. Тому от ще таку перевагу ми отримуємо. Ну і хотів би, не знаю, чи доречний цей слайд, може не зовсім до цієї теми, але хотів би все-таки пару слів сказати, що вибираючи будь-яке обладнання, а зараз я говорю про насосне обладнання, я вас, як от серед вас, я думаю, більшість все-таки організацій, які експлуатують обладнання, приймаючи рішення того чи іншого обладнання, пробуйте, як сказати, або розумійте, що ви платите не просто за обладнання сьогодні. Тобто воно може коштувати сьогодні 5 тисяч євро, 6 або 5,5, але все-таки оця ціна обладнання – це лише 5% у тому, що ви заплатите за весь цикл його експлуатації. Основне, що коштує в обладнанні – це електроенергія, яку ми використовуємо за життєвий цикл того чи іншого насоса. Тому якби енергоефективність і саме економія електроенергії – це от той шматок, де ми можемо отримати найбільшу економію. І я думаю, якщо ми будемо з цим підходом аналізувати те чи інше рішення, в результаті ми будемо робити правильний вибір. Останній слайд уже, я наскільки пам'ятаю. Можна вас попросити переключити щось, ця штука? Ну і знову-таки про ту систему, про яку я сьогодні розповідав, контроля тиску, що да, ми говоримо про витоки. Ось бачите, мої колеги Данія, Польща, мабуть, мають більше досвіду, бо це перекладена інформація. Вони говорять про те, що десь до 15% можна зменшити витоки за рахунок впровадження системи стабільного якби тиску у споживача. Да? Ми економимо електроенергію, ми знижуємо частоту поривів трубопроводів, і, звісно, ми експлуатуємо якби обладнання, систему в більш стабільному, якби неаварійному режимі. Так, це все. Дякую за увагу. Якщо будуть питання, будь ласка, радий буду відповісти. Дякую.
Перепади, я думаю, що не чути.
Поки так.
Геодезичні перепади, тобто на різних відмітках, що суттєво впливає на тиск на вході до споживача. Як вона ефективність роботи? Тобто один споживач може умовно мати 2 атмосфери на вході, інший, враховуючи перепад пізометричний чи геодезичну відмітку, на 2 атмосфери більше. Як такі системи?
Да, дивіться, якщо ми говоримо, що у нас і у того споживача, який внизу, і того, який вгорі, забезпечує водою одна насосна станція, то, звісно, ви цією насосною станцією маєте подати тиск, якого буде достатньо для верхнього споживача. У нижнього однозначно тиск буде надмірним. Як це можна з нашою системою зробити. Наприклад, 2 датчики, да? Але система все одно буде орієнтуватися на те, що по верхньому датчику, той, який у верхнього споживача, тиск був достатній, який ви хочете. Тут, можливо, Майкл може додати, як можна цю ситуацію покращити, використовуючи їхнє рішення від АВК для стабілізації тиску. Майкл, maybe you can add how we can, how you understand the question? Yeah, okay.
Yeah, I was thinking while Oleksiy was doing his presentation, it's not a question about either pumps or valves. It is a question about both. Because if you work with a water tower, for example, then you lower the pressure, but the water from the water tower will then increase the pressure again. So there you need a control valve to keep the pressure on the water tower according to what the pump is delivering in pressure. Second, also, if you have a very hilly area, I mean, a pump generates a pressure, and a pressure reducing valve will destroy the energy used by the pump. So you have to calculate, you have to look at your geography. Do we have any high points, or is it flat like a pancake? And if you have high points, then it's a combination about pumps and valves that will take care about the high points, because otherwise, as in my case, the water will come from, say, 40 meters above and down to say 0. Then you will add 4 bar to the water pressure in the lower. And then again, you need a control valve in order to. So it's a combination about pumps and valves if you have a hilly area or you're using water towers. And actually, we conducted a project in Denmark with pumps and valves. And our challenge back then was to have those two communicating. So if the pump raised the pressure and then the control valve reduced the pressure again, that would make no sense. So the job was to combine the signal and have those two to work together instead of against each other.
У мене питання при втраті зв'язку з датчиком. Як реагує контролер?
Дивіться, да, дякую. Датчик – це для накопичення інформації, тобто жорсткого зв'язку, коли в нас щось відбулося в контрольній точці, ми це називаємо, насос відразу не реагує. Тобто давайте уявимо так, датчик накопичує дані, передає в систему, далі він знову накопичує, передає. Якщо щось помінялось, система плавно дуже адаптується до цього. Якщо 1 день або 2 дня, у нас в Житомирі таке було, бо там датчик стоїть в зоні, де інколи, ну, скажімо так, щось включають, і він дійсно не передає дані, то просто система буде працювати по останньому алгоритму, тобто останньому побутованому алгоритму. Як правило, цього ніхто не помічає. Тобто ми бачимо, що дані 2-3 дня не передались, водоканал розбирається, чому, може там, не знаю, вони за пакет сім-карти не заплатили, а можливо хтось щось там включав і якби були якісь поміхи. Да? Але ми будемо про це бачити, що дані не оновлюються, але при цьому у нас система ж не помінялася і в принципі такого, щоб там скаржились споживачі або тиск був недостатній, або ще, такого не буде. Вона просто буде працювати по останньому побудованому алгоритму. What is the price of the system? It's question to me, okay? Дивіться, система DDD фактично це, я вам показав вимоги основні до її роботи, але фактично це шафа керування з розумним контролером. Так я назву. Да? Тобто, якщо в нас є все інше, насоси однакові, насосні станції, частотні перетворювачі, вам потрібен, нагадаю просто, витратомір, вам потрібні 2 датчики тиску мінімум, і вам потрібно, насоси у нас є, все, да? І нам потрібно тільки додати оцю розумну шафу керування, кілька датчиків віддалених і модуль для сім-карти, щоб передавались дані. Я так скажу, це менше 10 тисяч євро. А вже там треба дивитися по потужності насосів і так далі. Але це при умові, що насоси і частотні перетворювачі у вас уже є. Ну, тобто, ви зрозуміли. Ну, нам часто питання задають, чи можна цією системою керування керувати насосами не Grundfos, то, в принципі, відповідь так. Звісно, нам цікаво запропонувати комплекс і насоси, і систему керування, але якщо у вас вже стоять насоси іншого виробника, з іншими частотними перетворювачами, то цю систему можна додати до того набору, який у вас вже є.
No, if you're asking for the price, the example that I showed, the inlet chamber plus valves, control box, pressure sensors would cost you, say, around 4,000 euros. Actually, we should have had one more presentation in this panel, namely water meters. And in this instance here, smart water meters. Unfortunately, the guys that should do it is getting sick or was sick, so he couldn't come. Normally, or if you have a mechanical meter, then once a year or once every half year, you need to go and read the meter, sign a bill or a paper, and send it to the water utility. And then you get paid for the water that you deliver to the household. With a smart meter, then you can have basically the information hour by hour, day by day, week by week, month by month, so that you'll be able to know much more quick how much water did we actually sell in this month, in this week, etc., depending on how often you want to have these data. So that will be the normal way that the water meter will give information. Customer service will write a bill, send to the consumer and ask him or her to pay the bill. But in this case here, the water meter, the smart water meter, will also act as a, first of all, finding leaks. You remember this morning Fleming told that most of the leaks are occurring on the connection between the main line and the house connection or service connection line. And the smart meter is working on sound. And so, and you heard a lot of sound noises from Nikki. And the smart meter, one of the jobs for the developer was to exclude the sound of leakages, because they only needed to have the sound of flow going through the meter. But then all of a sudden they realized, hey, a leakage sound that we actually eliminated in the water meter, why not add it into the water meter so that the water meter can actually report leakages on the service line or on the connection between the main line and the service line. So now all of a sudden you can also use these smart meters not only to pay the bill or send the invoice to the consumers, but you can also have an indication of if you have leakages along the service connection lines. And based on this information coming more frequently, you will also be able to do your water balance and fill out this IWA water balance sheet, because now you know how much water is flowing in to the DMA, how much water did I sell, where is the difference? So water meters nowadays can add more than just making a bill for to the consumers. It can also reduce your non-revenue water. I'm not an expert, so I can't give you a lot of more information. I'm not sure I can answer any questions, but any questions about smart water meters, I will take them, or I hope I can answer. So the last panel for today would be about digitalization. We will continue last panel for today, and clean drinking water. We have 3 panelists in this panel here. We have again Fleming from Aarhus Water, and we have Klaus Høgh online again from NIAS, and Simon Damkjær from Seabrain. So I will give the floor to you, Fleming, as a starter. Please, the floor is yours.
Thank you. for those of you who heard my previous presentation, basically, I continue with the same topic, but more in the view of digitalization. So my perspective on digitalization is non-revenue water and how we can reduce water loss by digital solutions. So basically, I showed this one in the previous presentation. So now we are more in the data part of how we can reduce water loss in the system. And of course, you need to have, when we talk digitalization, we need to have data and sensors in the system. You need to have a backbone of digital pipeline registration, a georeference system, and then you can start having data online from different sensors in the system. In our case, it could be like real-time data from the water treatment plants. Of course, we have the pipeline registration. Burst registration is important to fight water loss. And the best thing is that if you can have it in some kind of shared data platform where you can access all this information and visualize it. This one I also showed in the previous presentation, but basically when we talk non-revenue water, we are talking about from the water treatment plant until the consumer, what is lost in that part of the water supply system. So in our case, having a digitized system starts with having online data in the water treatment plants. This shows the SCADA image of one of our water treatment plants. At the left side, you can see the wells. You can see how many of the wells are in operation and what is the production from each wells. That can be seen real time and online in our system. And then we have the filter section of the water treatment plant, and we have the storage tanks, clean water reservoirs out at the treatment plant. We have level sensors in those, for instance. We can monitor the turbidity, the particle content in the water, a number of water quality sensors out there too. And after the clean water reservoir, we have the outlet from the treatment plant. And in this case, it goes into two parts, which is also something that needs to be noticed because the lower outlet from this treatment plant is by gravitation. So basically it flows from this storage tank to the city, whereas the upper part is by booster pumping because it supplies water to a part of our system that is higher than where the water treatment plants is. So there you need to boost the pressure. And all these points here, we have online information on how much is produced. For instance, in your part, you can see only one pump is in operation there, the P1, and it produces some cubic meters, this pump. So it's probably in a time with low consumption in the network since only one pump is not in operation. Oops. Yeah, and of course we have discussed the concept of DMAs and sections, and I don't want to spend much time on that, but I can tell you how it works in our system, because basically we come from a system, the picture to the left, where we had a number of pressure zones. We have some terrain in our city, so we have higher areas and lower areas. And of course, we need to make sure that the lower areas close to the harbor of our city, they don't receive too high pressure. So if we did not have these pressure zones here, the pressure in the lower part of the city would be much too high because water flows by gravitation from the higher parts of the city. So you can see, for instance, up north, we have a pressure of 125 meters above sea level. And in the lower parts of the city, we can supply around 50 meters above sea level. And this was a picture we had before. And now we have moved into the picture you can see on the right side, where we have a big number of sections and DMAs, where we only have very few inlets, maybe one or two inlets to each of them. And we have valve chambers, meter chambers, like the picture you see to the right. So we have a big number of those scattered around the city at the inlet of each of those DMAs. and each of those have a water meter and a pressure meter and maybe a temperature sensor. And we can also introduce water quality sensors if needed. Those chambers are big enough to equip them with more sensors that can transmit data online. And basically, this is the picture you could expect from one of those DMA's wells. You can see at the bottom, the red curve is the consumption curve. The way we monitor water loss in our system is that we look at the nighttime consumption. So basically, that red curve should go to the same low level every night between 2 and 3 at nighttime, because at that time there should be close to no consumption in the area. We might also have other areas where you expect some consumption at nighttime, but we start to understand these patterns. And usually people, they have the same behavior day after day, and even most industries do the same thing day after day. So when you start to understand this pattern of consumption, you can use the nighttime consumption to see if something unusual is happening out there, and consumption suddenly rises, which could be a leak out there. So that was basically, and of course we also have a non-return valve. So we want, when we have transported the water into this DMA, we want it to stay in there. So we make sure that the water cannot flow in the opposite direction. So basically the backbone, where you need to start having digitalization is in the pipeline registration system. And we have a completely digitized system with a big number of attributes on each pipe. So, for instance, we can see what brand it is, the pipe. We can see the year the pipe was laid, and we can also see this. Everyone employed in Aarhus can access this information. So basically, our staff on duty, they have an online platform on a tablet or a smartphone where they can go directly into this system and also report incidents on the system from one access into the system. And in Denmark, I can also mention there is a national data model for pipeline registration. So we have a standard called the DK1 standard that all utilities in Denmark, they have the same data structure in their pipeline registration in the database. That also means that, for instance, contractors, when they do construction work on our system, they report directly into our system. So we don't have necessarily our GIS department processing data from the contractors, because they can report directly into the pipeline system because they know the data model and have the access to report directly into the system. So we don't it's not needed to pass through us, because we know that the quality reported from the contractors would be appropriate, because it's a common tool that they use for all utilities in Denmark. Since we have this register, we also know the age of our pipes. The oldest pipes we have in our utility, they are around 100 years old, but the average age of the pipe that we have is around 30 years. So we renew every year a certain amount of pipes based on asset management, condition of pipes, maybe dimensions need to be changed and all that. So we have plans for rehabilitation of the pipes that extends for many years out. So basically, we know by now already what kind of investments we need at least 10 years ahead from now in terms of rehabilitating the pipeline system. Yeah, and there you can see what kind of materials we have. Most of it is PVC, but nowadays most of the pipes we install nowadays are PE pipes. Then we have some older cast iron pipes, and we have Eternit is asbestos cement also. But those Eternit asbestos cement pipes is priority to replace them. So that is one of the priorities in our asset management system in terms of investment in the pipeline system, is that we want to get rid of all asbestos cement pipes. And we have had a burst reporting system in place since 1978. So since 1978, every leak and burst that has happened on our system, is stored. I think maybe in start it might be in paper sheets, but now it's in a database. So it's all stored in the database. So basically on the map here to the right, you can see the distribution of bursts in our system. And you can see since 1978, for instance, the lower here, the green one, is the burst that happened in the period from 1978 to 1982. That was about 1,000 bursts. So you can see that actually we have had varying during the years number of bursts, but that is also something that depends on general conditions of the pipes and something that we use for our pipeline replacement planning. So it varies from year to year, and you cannot really say it's going down, but there is also something where you need to find the economical feasible level of that, because you can invest much more in this and reduce number of bursts much more, but still maybe the business case would not be that good, because even though we lose some water in the burst, we must accept that we have a certain number of bursts in a peak utility. You cannot make it disappear completely. Yeah, you might be able to, but it costs huge investment to reduce a number of bursts to close to zero. This is just an example of our people on duty. They have access to a platform like this one. So when they are out on a site, they can report directly into our system any kind of incident they see out there. They can store photos. They can write text. So all the works that we have going on, construction works or repair works, all that you will be able to find in that system stored by the staff on duty. As a management, because when you have all this digital information in place and stored in a systematic way, you can start working with as management, which is basically identifying where you get the most out of the investments that you do in your system. It's a little slow here, so I think this one here, yeah. So this is more like a close-up of hotspots in our pipelines. So there we can see actually in this area at the picture at the bottom, we have certain parts of the system where we apparently have more bursts than others, and that is something that we can use as one of the parameters when we want to rehabilitate the pipeline system. And number of bursts also closely relates to kind of material we have out there. For instance, we can see we have a lot of PVC pipes, but they have very low burst frequency. On the other side, we have some limited number of old steel pipes, but they have very high burst frequency. So it's highly dependent on what kind of materials you have out there in the pipeline system. So storing all this information, we can start doing planning of rehabilitation. So we have a system that tells us, okay, probably in 2030, I don't know, these are a little old figures, but we can predict when we need to rehabilitate certain parts of the system. Of course, depending on the investment funds we have, because we also have limited funds for investment. So we need to make sure that the funds we invest in our system are done the best possible way and in the parts of the system where we get the best benefit of it. So that is what we do by pipeline rehabilitation planning. I think the concept of DMAs, we have touched upon that. So I will not tell you so much, but that's just an example of a DMA where you can see normal nighttime consumption at the lower red line, and suddenly something happens. The nighttime consumption rises. And in this case, it was a leak out there that we need to go out and find and repair. And we also have a system in place that actually does this monitoring in all our DMAs automatic. So this system can recognize the patterns that we have on nighttime consumption. And our staff on Tuesday, they open this system every morning when they go to work and see if there are any red lights in the system, meaning that we have an unusual nighttime consumption in a certain area. So they can go out, investigate what is the reason. It might be unusual consumption, but it might also be a burst or a leak. So they start identifying the reason for this higher nighttime consumption. I think there was a presentation on leakage detection, so I will not tell you so much about that. But of course, we do that also. We have staff doing leakage detection, also by the instrument that has been shown in previous presentation. We also have our own developed methods where we can basically, by closing valves, making very small DMAs and do very quick leak detection, because the trailer that you see here, it contains a small tank of water. So if we can isolate an area completely by closing valves, then we can put this water pressure on a fire hydrant and make our own pressure. And we can, by doing that, very efficient and very fast identify leaks in the system. Yeah. And I think also the previous presentations also have touched about the advantages of pressure management, because of course when you have sections and DMAs in the system, it makes it possible for you to do pressure management and maybe reduce pressure variation, lower pressure at nighttime, because pressure in the pipeline system closely relates to number of leaks and bursts. So if you can reduce pressure, that is a major advantage. I have been working here in Lviv since the last year or so, and I know pressure here in general is like 5 bar in the water supply system. So that's very high. So I guess for a city like this, it could be a huge advantage to reduce pressure in some parts of the city where it's really not needed for water supply. Thank you.
Klaus, can you hear us?
Well, thanks again then. And let me try then to take over and follow up further on digitalization and how to utilize data. I will show you some concrete specific examples of how to utilize a digital twin of a water supply network, and also how a digital twin of a water supply network is built. The principle is built here on what we call the Leakman concept, the Danish concept for making efficient non-revenue water management and water loss control, but it is actually capable of doing more than just that. It's more or less takes the idea that, continue what Fleming said, that well, we have a lot of different data systems that has more and more valuable data inside them. And if we can start somehow to integrate these data, use them across each platform, then the data will actually start to generate additional value. So, and that also allows us to do this more and more automatically using digital tools. When we implement a digital twin, then we are into the more heavy end of digital transformation. A digital twin is something that can actually support when you shift from manual or empirical knowledge-based operation to data-driven decision-making. But to reach that point is a long story. You need to have all your data available. Each data source is available in a separate system. So we need to start by creating the data interfaces to each of these systems. Then when we have an interface to the system, then we can actually get the data out of it, out of each source. And then we can start to do some integration with the data. We need to have some kind of advanced data management. We need to build up like a data lake or a big database containing all these data that are now integrated. Then when we have all the integrated data available, then we can start to do advanced system modeling and start to create a model of our network. And as we then progress, we can actually move ahead and start to do real-time or very near real-time modeling and near real-time simulation. And when we can start to simulate real-time, then the next step is to actually try to forecast and optimize what is going on or what is going to happen in the network. So this is the whole platform that you have to build behind a digital twin of a water supply system. And then in the end, to support the operators in actually being capable of applying such a system, such a digital twin, then you need to apply some monitoring and visualization so they can actually utilize it as a extra tool to actually take qualified decisions to change the operation. It can also be used in an offline mode to investigate what would happen if I do like this before you actually do it, and then you can see how the system would respond. Here you see a screenshot to the right where you are looking at a supply network where you see all the pipelines. You also see all the customers as small dots. Bigger dot are bigger customers. Then you can see there are some noise loggers installed. They are actually integrated with this system here. Now, if I had a noise logger that would be orange or red, would mean that that has a warning for a potential leak at that location. And that means you can directly zoom in one digital twin. You can zoom into that location, see you have a noise logger in alarm, which may be a leak or a leak alarm you have to inspect. And if you have 10 or 20 of those, then where to start? Well, a digital twin can aid you in that, because if you have it in a digital twin, it will show you, okay, this noise log is very close to a pipe that has a very high flow. This is a critical pipe if it bursts. So I maybe should prioritize to check that leak alarm first. It can also be because we have integration with the customer information system that I can see this alarm is very close to a critical customer. Could be a medical clinic or something like that. So maybe I should prioritize that leak because it'll be more critical if the medical clinic is out of water than if a normal small, domestic area is out of water. So this way, a digital twin can combine all the information into a visualization that can actually support the operators in taking better decisions. But again, getting there is difficult because the data, as Flemming also showed before, are available in different databases, in different platforms, different systems. For example, in this is just showing a case where we have 6 data platforms or systems. We have the GIS, which is typically a GIS system, which is topology. We have a customer information system. And in some cases, customer information is more than one, because you can have a billing system, you can have your meter registrations, you can have AMI, you can have AMR with remote read meters and so on. Here I have just grouped them all into one, but it's important to see that we have both the customer data and the meters. So we have information about the customer meters. We have information about the customer's type and how much water they use. We have SCADA, is very important for online. We have some of network control. We know where the pump supply, where the sources are, where the pumps are, where the valves are. We have a work order system with planned maintenance and unplanned maintenance. We can see where has there been a maintenance work, what kind of a maintenance was it, and we can also see the same for unplanned maintenance. Customer complaints. It's important to know where you have reports of leaks, where you have reports of low pressure complaints and so on. And then finally, we also in this case have access to a water quality result database. That means all the sample results of water quality samples are stored in this database. Now, to be able to combine all this together, we need to make sure that every asset, every component, every record has a location so that we can assign it to a location in the network. If we have a customer with a high demand or a critical customer, well, if we want to warn this customer, we of course need to know where he is located. And the same thing is if we have a record of customer complaints and we want to use it to actually find areas with a high number of customer complaints, we cannot do that if we don't have an accurate location. But this is not the reality. In many systems that is built up today, there will be a lot of conflicts when you look across this. You will have a customer who has a meter ID that doesn't exist in the meter database. You will find a work order that is registered on a pipe that does not exist in GIS, and so on. And this is very normal. This happens in all utilities because these various platforms or systems here have been implemented over the last 40 or 50 years, and has never, in many cases, been made a consistency check that actually checks that all the records can be actually integrated and cross-referenced across the data sources. So this is always a big challenge when you have to build a digital twin, that you need to make this integrated connectivity model that fits with this one. And you need to be able to give a warning about the records that doesn't have a reference to the rest of the system. So do you have any customer complaints or work orders that are unknown? You don't know where they have been carried out. You just know there has been a leak repair, but you don't know where, because then the information is useless in a digital twin. But if we have all this data, then we can start to combine them. Data sources, main pipes, sector main pipes, service pipes, all the valves, regions, pressure management areas, district metered areas, customer demands and meter information, water quality samples, work orders, SCADA monitoring locations, customer complaints. Then you can build a hydraulic model that contains all this information, pipe network, SCADA, how much is produced, how much is used, and so on. And that means if you have a real-time hydraulic model, then that real-time hydraulic model will, let's say, every 15 or 20 minutes, calculate what is the flow and pressure in every pipe in the network. So you will actually know the hydraulic state of your entire system in almost real time. And that means also you can utilize the data to build a benchmarking or performance monitoring system. And then the hydraulic model can add additional data into this benchmarking system or performance monitoring system. For example, in a hydraulic model, which I'll show you in a little while, will give you what is the expected water age in every area of the system. It will also give you in a network, and you will typically know the pressure at the inlet to each DMA. And then maybe you'll have one pressure sensor inside the DMA that will give you the pressure at that one location. But if you have the hydraulic model running, then at every time step, the hydraulic model will also provide you information about what is the minimum pressure inside the DMA at any location, and what is the maximum pressure at any location, which can be useful information, and which can be used for the online performance monitoring. Because then this is a case where the meters are being read manually every month, approximately. Every meter is being read 10 times per year. The SCADA data are coming in every 5 minutes. And then there is a procedure for calculating the water losses. It's an estimating all the non-meter demands. There is a methodology to estimate the customer metering errors and so on based on IWA standards. So it means that here you see that every month for more than 100 DMAs, there is an automatic calculation of the water balance. And here it just shows you 4 components. The system input coming from the SCADA system, the authorized consumption coming from the billing system, combined with records from the water company of water used for pipe flushing and fire flows and other authorized consumption that is not in the billing system. And then the difference is the water loss. And this water loss is then divided into real losses and apparent losses. And the apparent losses is calculated again automatically every month by looking at how old are the meters inside each DMA. Here we're looking at all of the pressure zone, one big pressure, where you go into the DMA, the pressure zone, and select the DMAs inside, and then you can see how each DMA is performing. And here we can see an example of a DMA where they have actually had a boundary valve is open during some periods. So the DMA is actually exchanging water with one of the other DMAs inside the pressure zone. And all this information suddenly becomes visible for the operators. It also means that with this accurate pressure calculation, then I'm just zooming in on one pressure zone here, reduction, there's one inlet to this pressure zone, which is here in the upper right corner of the zone, right here. And I will show you how just when this system will be running, this facility can be used for offline studies or online. But if this one was running online in the control room, which it actually is, then you will every hour or every time the model has made a new update, the operators will be able to see how the pressure changes. And I made a small movie of that. You see here, you see water is coming in at the top during the day. There's some variation to the pressure. And then suddenly at 8 in the evening, and this happens almost every day in this pressure zone, at 8 in the evening, this lower area here drops below 1.25 bar. And 1.25 bar is actually set as the service level. This is the service level that the water company has to provide at the start of all the service pipes. So that means every day at 8, when you have a high flow, the pressure in this area here will drop below the required service level. So you will see that from the digital twin as it's operating. You can use it to zoom in. And as you zoom in, you can see that which customers are located in this area. What is the minimum pressure inside this area where we have a pressure violation? We can see that the pressure is just below 1 bar. So the violation is minor, but it's consistent day after day. And we can see what the inlet pressure is to this DMA. So now there is 2 options. The operators can look at this and see, okay, if we have a pressure reduction valve here at the inlet to the DMA, then we have to adjust the setting here if we want to get rid of this problem, or we have to go all the way back to the inlet to the pressure zone and increase the pressure a little bit here at the inlet to make sure that the pressure in this far corner of the pressure zone has adequate pressure. But we can also see that we only have to increase the pressure for 1 to 2 hours every evening from 7 to 9, I think. Then it will be acceptable. So this is a really strong application of a digital twin. And while you're here, before you make the decision, you can actually, since it's also connected to the billing system, you can actually get an idea about which customers are actually located here. You can get a report of the customers, which is dimmed here because it's confidential. But you can then see the account ID and the meter number and the premise type. And you can see how much annual demand they had in the previous year for each of these customers here. So you can also see if there are any critical customers here that would suffer from having a low pressure before you take your decision of what to do. So this is one really advanced example of having a digital twin running in the operator room or control room for a water supply. Similarly, it cannot just be used for leak detection, pressure management. You can also monitor the water aids. Because most of these hydraulic modeling tools, they include facility to actually calculate water quality. And again, a first simple example is to monitor the water aids. And we can do this again, start the simulation, see that here water is coming into this pressure zone. We can see how the water is propagating around the network during the day. And then, of course, we need to let it run for a few days to stabilize. But then we will be able to see if there are any areas inside this pressure zone where the water age becomes very old. Do we have some loops that are not hydraulic sound, so that the water is just going back and forth or running around in circles, becoming older and older without being used? So this can actually be used to identify some some high-risk areas for having poor water quality if the water gets very old. And then finally, if we have such a completely different, now we're not looking at the online model, but we have all the data available in such a from such a digital twin. And then we can start to look at, in this case, this is a feasibility study from Kuala Lumpur in Malaysia. Here we did a job 1 year ago where we are making a feasibility study to assess the potential of implementing pressure management on their transmission pipes and transmission system and on their distribution system. They have more than 200 locations in their transmission system that is similar to what you see here. They have a big pumping station at the water treatment plant, which is pumping water to a big reservoir, a service reservoir, and then you have a demand area downstream the service reservoir. And they are just this pumping station is just running by on-off when within a minimum and maximum level of the reservoir, just running. If the water reach the minimum level, start the pump. If it reaches the maximum level, stop the pump. And that leads to the red curve you see in the bottom right, that the pumps are running up and down at a specific frequency and the same profile every time. If you have a really intelligent digital twin where you have a forecast of the demand, you have the electricity prices are coming into the system. You can have variation in electricity prices. So, and you allow the digital twin to not just utilize to not just pump when it reaches the top and bottom level and not pump full speed, but try to balance it so that you will instead of just hitting start and stop, you try to optimize so that it fills the reservoir within the minimum and maximum in a way that costs the least amount of electricity. And in that case, it leads to the blue curve here that actually over 24 hours, you will have one cycle less. You will run a little slower, a little longer, and you will not fill the reservoir to the maximum every time. You will stop a little bit before the maximum allowed, actually, because to fill the reservoir fully requires more pressure, and this is not feasible. And in this case here, it leads to a reduction. The feasibility study showed a potential in reducing the electricity consumption by more than 70,000 kilowatt hours per year, which is significant. And then you can have the other situations, which I showed you an example of earlier, where there was a pressure optimization installed on a DMA, where you have to know inside the DMA where do you have the minimum pressure, and then you have a valve at the inlet. And this can both be a valve in be an inlet where you boost the water, or where you reduce boost the pressure, or where you reduce the pressure. It will work in both cases. But you want to make sure that the pressure inside the DMA at one customer where you have the lowest pressure always is above a specific target level. And this is then another kind of simulation. Here you need access to all the customer data, and then you can actually run this simulation to find out, in this case, how should the pump run to optimize the pressure. We have a situation here where the pressure is higher than required. So how much could you actually reduce on the pumping? And we also investigated some cases here in this feasibility study. And this case here says that the average zone pressure will be 34 meter, which is a reduction in pressure to was almost 48, would lead to a 48% reduction in the background leakage. And then that depends on what is then also the electricity cost of the pump will run a little more efficient, and how much water will we actually save. So this was really an interesting study we made a year ago, and they are just now in process of ordering and starting up to implementing this in more than 200 areas. So this will be quite interesting to see what happens, how the total result will be over the next 2 to 3 years. That was my presentation about digital twins in a water distribution network.
Thank you so much, Claus. And again, please stay online for questions afterwards. So next speaker will be Simon Damkjær from ZBrain, and we are still in the digital world, I guess.
Okay, good afternoon, everyone. And I am the last speaker of today, so thank you, everyone, for having sat through all of these wonderful presentations. I know it's been tiring, so I hope you'll still follow me, but thank you. I'm Simon, and I work for a Danish GovTech company called ZBrain. We don't specifically work in water. We work across all sectors. And today I want to share a small analysis on the Ukrainian water sector and highlight how digitalization is able to play a critical role in strengthening your governance, resilience, and the EU alignment, such as the EU Water Framework Directive and the Urban Wastewater Treatment Directive. And I think the one message I want you to take away from what I will talk about here is standardized digital data governance is the fastest pace to achieving water resilience. Ukraine's water sector, there's no doubt it's under incredibly extraordinary pressure. 70% of infrastructure is more than 30 years old, and depreciation rates are about 60%. Losses are staggering at up to 50% of treated water never reaches customers. And it not only undermines service, but it also makes it weak to have a financial basis for utilities. Chronic underfunding and the difficulty of attracting talent in the sector is also another challenge. And at the governance level, permitting and inspections are fragmented and still handled very manually without integrated platforms for data, monitoring, enforcement, or reporting. The result is lack of reliable data for national oversight and for EU-level compliance reporting under directives such as the Water Framework Directive. So we must be clear, Ukraine faces a dual challenge of war recovery and EU integration. These combined pressures create urgency, and the sector needs to move into a quickly standardized, data-driven digital governance approach. So to give you a bit of a background on Denmark's digital journey, we are one of the most digitized countries in the world. We're ranked as the #1 country in the world in e-government, and we've built a long tradition of digitalization across our government. At the Danish Environmental Protection Agency, who is one of our customers, everything has now been fully digitalized. Permits, inspections, subsidies, and reporting are all handled in a single integrated platform that ZBrain has produced. And it means that decisions are faster, processes are transparent, and enforcement consistent by all civil servants. And it's not theory, it's practice. And as it stands now, digitalization in environmental governance is possible and scalable, even in Ukraine. And these lessons, I think, are relevant and for all who is attending both upstairs and here. What does it mean? An end-to-end solution. The kind of digital transformation I'm talking about covers the entire chain of the Environmental Protection Agency. Permitting can be handled digitally from applications to approvals. And when these elements are integrated into one system, the effect is more efficiency. It also creates traceability, and Environmental Protection Agency, who is one of our customers, Everything has now been fully digitalized. Permits, inspections, subsidies, and reporting are all handled in a single integrated platform that CBrain has produced. And it means that decisions are faster, processes are transparent, and enforcement consistent by all civil servants. And it's not theory, it's practice. And as it stands now, digitalization in environmental governance is possible and scalable, even in Ukraine. And these lessons, I think, are relevant and for all who is attending both upstairs and here. What does it mean, an end-to-end solution? The kind of digital transformation I'm talking about covers the entire chain of the Environmental Protection Agency. Permitting can be handled digitally from applications to approvals. And when these elements are integrated into one system, the effect is more efficiency. It also creates traceability and across the entire governance system, regulators, utilities, and government officials can see the same data in the same time. And I think this is what enables transparency and ability to act and work in a uniform way. So to take it to the level of Ukraine, the strategic importance of a proposed digital standardized solution to the water sector. It supports compliance with the key EU directives, the Urban Wastewater Directive, Industrial Emissions Directive, and without digital monitoring and reporting, it's almost impossible to generate the data needed for compliance. Secondly, it also provides the transparency that I mentioned before and accountability. So we have everything from citizens to regulators and donors that all have confidence in a system. And finally, resilience, which is one of the key themes of this forum. Resilience is strengthened by embedding governance into digital systems, reducing vulnerabilities and making enforcement predictable. On the slide here, I've just, to build a national backbone of digital registries for wastewater asset management and SMEs, as we've just seen by our colleagues at NIRAS and Aarhus Vand, Ukraine needs data-driven governance. And that means defining KPIs, such as non-revenue water, which has been discussed today, but also compliance and tariffs. All of these things need to be tracked and consistently across all utilities. And the solution must also be built on a standard software platform that can be rolled out quickly across all the different utilities without having to design a new system for every utility. And like I said, compliance with EU directives must be embedded from the start. So Ukraine is not just recovering, but Ukraine is also leapfrogging into a modern, resilient digital government. I said program tie-in. Yeah, I think it's better if you just do it, please. Thanks. That way, I will put this down here. Yeah. So, as I said, it's all about rehabilitation and resilience, and digitalization is central to both. And we spoke about the governance backbone. It's also an opportunity for dialogue. Denmark has experience. We are one of the most transformed digital transformation countries that have undergone a long digital transformation. And Ukraine has needs and forums like this one that allows us to exchange ideas on how digital solutions can speed up recovery in a European style. So next slide, please. So just to tell you a bit about CBrain, we, like I said, we're a GovTech company and build standard software for governments and are expanding to work with utilities now. In Denmark, 17 out of 17 ministries, actually now 19 out of 21 ministries and 75 agencies use our platform for their work, which means that our solution is not theoretical, but it is a way of running everyday business as a civil servant. The approach, as I have emphasized here, standard software is it's instead of coding new IT systems every time, we just configure standard modules to support policy, permitting, inspections, and reporting. And it allows for decisions, political decisions, to be implemented and executed much more consistently and faster. Next slide, please. So the curve here is the digitalization journey of Denmark, but actually of any country. It comes in 4 waves, where the first is the front-end digitalization. Most countries have this, where you as a user, in both step 1 and step 2, can go in and you can use the internet to fill out forms for applications. If you need a permit, for example, for drilling. However, where it becomes more complicated and more data-driven is the last 2, where decision-making and case handling by public and civil sector servants are able to perform all their work online. Agencies can talk to each other, and artificial intelligence and machine learning is integrated into the work of a civil servant every single day. Next slide, please. So I will just, sorry, this presentation was made very quickly the other night. Yes, so for example, a core element of resilience, like we saw on the previous slide, is having a registry of assets. In Denmark, we have, our company has digital documentation of about 20,000 overflow and discharge outlets. So for each one, there's an inspection history, incident reporting, and planning of data. And everything is managed in one single system. So this gives regulators, utilities, full transparency, and it means that problems are identified and compliance can be demonstrated. And I think this is also the kind of tool that a country that is rehabilitating its water sector could very well benefit from easily rolling out across all sectors. Next slide, please. And moving on with the inspections, another pillar, like I mentioned, is the use of artificial intelligence and automation. However, they are only efficient if they're built on standardized data. AI can help inspectors by identifying high-risk sites and support risks-based inspections of wastewater. But it can also help to bring consistency because the system can learn from previous decisions. But without standard registries, AI is just noise. With registries, it becomes a tool, it becomes a powerful assistant that saves time, reduces cost, and supports compliance. Next slide, please. Data-driven benchmarking is also one of the strongest arguments for digitalization. We mentioned non-revenue water is typically 1 to 5% with a legal maximum of 10% in Denmark, I think has been covered by previous presenters. And as I started off by saying, in Ukraine, it's up to 50%. But without reliable data consistently treated, it's impossible to close this gap. Yes, so again, standardized platforms with common KPIs that every utility can report in and access. It's also a way to attract donor funding because donors want to see data. So I think benchmarking makes efficiency measurable, and it gives credibility to ambitions of a reform. Next slide. But really, it's not about building one IT tool here and another one there. The vision is about having a standard digital backbone for governance for all government departments, including utilities and regulators. It means permitting, inspections, and subsidies all happen inside this platform called F2, which is the platform used by the Danish administration. And anything from permitting, inspections, subsidies, reporting and monitoring all happens within this platform. It means that there is no silos, there's no duplication of work, and there's no conflicting data. Silo thinking in the water sector is one of the biggest challenges I have experienced, and everyone agrees. So if we are able to work on the same platform, it works. And to just show you, in Denmark, these are all the ministries and agencies as well as municipalities, and one utility that runs on the F2 platform by Seabrain. Next slide, please. We also have a global presence, and we hope to be able to put Ukraine on the map next year if there is a good dialogue that continues. Prepared and tired. So I want to mention, in relation to the previous presentation, which was, I think, amazing work that is possible to do. But we take a little bit of a different angle because we actually want to disrupt digitalization and digital transformation, because the slide shows why standard software is disruptive in digital governance. In a custom-built software, up to 90% of the budget actually goes to consultants who write the code. And this results in a high cost, long delivery times, and heavy dependency on external suppliers and consultants. No offense to the consultants in the room, but we think it can be done cheaper. And through standard software, the cost is split very, very differently. About half goes to actual software and half for configuration, which makes it 3 to 5 times cheaper and faster to deliver. And we think this is critical. Speed is vital, urgency, and we cannot start building systems from scratch again and again and again, but can use 20 years of best practice. Yeah. So next slide, please. So faster implementation, lower risk. You don't have to start from scratch, and you benefit from what has already been tested elsewhere. In Denmark, the most digitalized public sector in the world, and it's future-proof. Updates and upgrades are delivered continuously. Next slide, please. So just to take the debate about custom versus standard software, a custom-built IT system is full of coding. It has lots of time and effort spent on developing unique solutions and creates the silos that we're working to break down in the water sector, and it's incredibly hard to scale. A standard system, as seen on the right-hand side, by go back to the, is mostly about configuration. It's built to be interoperable, to connect across agencies, and can be reused in new areas, new countries. Yeah, so that's the real power of standardization. It not only saves time and money, but it also creates integration across all government institutions. Next slide, please. So the best way to think of standard software, including in the water sector, is the Lego principle. So Lego being Danish. With standard modules and components, it's possible to build many different solutions, and they all fit together. That's how we need to build digital water governance. It's not a one-off custom-built solution here by one utility and another by another municipality. It's about reusing and assembling modules for governance and decision making. Yeah. Next slide, please. And this is, yes. Why, yeah. Why does Ukraine need standardization now in the water sector? Because delivery is in weeks from political decision. It's in weeks, it's not years, it's not months. And it ensures EU compliance. Next, please, slide. Yeah, let me just go back, because I want to show you what we've done with the Environmental Protection Agency in Denmark. The slide shows how the EPA moved from paper-based systems through digital workflows to become completely paperless. We call it a paperless ministry driven by data governance, data-driven governance. The important lesson here is that it's a journey. A digital transformation is a journey, by all agencies, regardless of what area you work under. But because standardized solutions already exist, if Ukraine was to start thinking about its national digital transformation strategy, it's not impossible and it can really leapfrog. Next slide, please. But just to give you some measurable impacts on how the Environmental Protection Agency and all their processes went digital. They have over 253 different properties that a civil servant sits and does case handling with, but they actually fall into just three types of processes: inspections, grants, and subsidies. We can see here that 17% productivity increase by taking control of the process, being able to work digitally is the data that shows 5% in case management. Yeah, anyway, next slide, please. Water related, the solution also pays out grants for drinking water, water protection, where grants are given to protect aquifers. Applications are digitally assessed. The criteria are transparent and priorities are based on integrated GIS data. It creates fairness and trust in the system. And again, for Ukraine, similar digital platforms could help channel scarce funds into the most effective investment. Next slide. The same goes for wetland restoration in Denmark, grants, and lowland restoration. Digital systems manage grant applications that prioritize based on the ability to extract CO2. Next slide. And a third example is lake and river restoration, where digital platform helps manage, again, the full chain from planning and funding to implementation and monitoring of restoration. Next slide, please. Dredging is also, permitting is a complex, dredging permits in Denmark are also fully digitalized. The process has traceable actions across all agencies that work on the same platform. And again, for Ukraine, such a complex multi-agency process could be digitized and make its governance much stronger and predictable. So yeah, next slide, please. So just to comment on the previous presentation on digital twins, promise and pitfalls. There is a lot of talk about digital twins in Denmark, and they do have promise, as we've seen in the previous presenter, for simulating flows, optimizing leakage detection, energy use, and planning. But the pitfalls we need to be aware of. Because if every city, every oblast, every agency starts to build its own bespoke twin, then again, we risk the silo fragmentation and the costs are very high. So digital twins are able, online, to create real value, but they must be built on national registries and standard software. And that's where the data collection becomes so crucial to work with what we have, but also identify what is missing. Next slide, please. And then a national registry of assets within the water sector is also not only useful for inspections and planning, but it's also, as we are in a time of hybrid warfare, it's essential that critical infrastructure, which is a target, can be defended, and all agencies and regulators must work with the same standardized data. So a national registry would allow coordinated inspections, shared situational awareness analysis, and rapid response. So it's not just resilience, but it's also about defending critical infrastructure, which is so important and in this country. Yeah, next slide, please. Yeah, we are nearing the end. So it doesn't stop at water. The platform can be used with water, wastewater, energy, environmental decision making. And the copy and adapt is basically is this thing I was talking about, modules and Lego bricks, where you copy the best practice and then you adapt maybe the last 5%, because governance at the end of the day, public administrations work across the globe very, 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 very similarly. An analysis we've made shows that about 90% of all the work that a government does, administration is the same. It's just at different levels in terms of its integration. So yeah, next, yeah. So yes, I think that a phased approach, piloting, adapting, and then scaling up, this is just theoretical, but it's an illustration of how a structured rollout could be done. And Ukraine doesn't have the luxury of long timelines. The challenge is to compress these phases and move faster, right? So standardized software is going to deliver this solution, if possible. And I think I will stop here. Next slide, please. Yeah. Yes. So to sum up, Ukraine does need to choose standard software over custom built in its decision making, is my recommendation from 20 years of experience working in the Danish digital sphere. To build governance, it must be data-driven and have benchmarking and transparency involved, which is what our good friends at Aarhusvand and NIRAS have been doing. And it needs to use artificial intelligence, but only in a secure standard environment. So national registries must ensure resilience and defense against cyber attacks. So yes, next slide, please. Yeah, so this is my contact if anyone is interested in discussing more about the possibilities of digitalization as a concept or in practice. We're very happy to talk primarily in the water sphere, both with regulators, but also utilities. So thank you very much.
Я вибачаюся, ну, мої запитання два, але будуть до попереднього доповідача, якщо можливо. Питання стосується окремо виділених зон з оптимальним тиском, але в цих зонах з оптимальним тиском є будівлі багатоповерхові, більш 9-го поверху, і для їхнього водопостачання передбачаються станції підвищування тиску. Моє питання в Данії, хто опікується такими станціями водопідкачки, підвищення тиску, хто є відповідальний за ненадання послуги з водопостачання верхнім поверхам, багатоповерхівим будівлям в разі негараздів з роботою цих підкачок? Це перше питання. І друге питання знову таки стосується цих самих зон оптимальних з оптимальним тиском і якості води. Всі присутні, мабуть, знають, що якість води формується з декількох факторів. Перший фактор – це якість води, яка виходить з очисних споруд. А на цю якість води може впливати якість самих санітарний стан і якість водопровідних мереж, якими транспортується ця вода, але і може впливати якість внутрішньобудинкових мереж балансоутримувача. Питання: чи є в Данії нормативно передбачена відповідальність за санітарний стан саме внутрішньобудинкових мереж і відповідно на можливі зміни в якості пов'язані з цим? Дякую.
Yeah, thank you for a very good question. I think Fleming should answer that because we had here during the break a talk about the pressure here in Lviv, and the reason why they have this high pressure is high-rise building. So I think Fleming should answer your question.
Yeah, I can say the service level agreement we have at the consumer side as a water utility in Denmark is that we supply a pressure of 2 bar at any connection. So that's even a high-rise building. So it's up to the owner of the property to make sure that it can reach the top floor in the building. So basically, they need to install booster sets on every like 5th floor or something like that to make sure that the water can reach the top of the building. It's not the responsibility of utility; it's the responsibility of the owner of the property. So that is something different, and I believe same kind of approach should be applied here, because having these very high pressures in the network is not good. So I propose that you consider doing the same here in Ukraine, but it's probably a matter of local regulation that you need to supply the top of the highest buildings. But I think it's not a good way to do it, because it's very bad for the network system. Yeah, I think the second quality, who is responsible for water quality inside buildings, if I'm understood it correctly. I would say Danish water regulation, basically we are responsibility to take samples at consumer end at the taps. So we are responsibility basically at the taps. But then again, I must say, for instance, people could install systems in their own houses that affects the water quality, and this has nothing to do with utility. So we are when we do take water sample at consumer end, it needs to be as close to our system as possible, because we are not responsible for what happens inside the building. It's not our responsibility. Basically, what we need to make sure is that what we deliver to the building meets the water quality criteria, and what happens after that, that's up to the owner of the building. So it's not our responsibility. Yeah, basically by law we should take what we call tap samples at the consumer end, which basically means that we need to go inside a house to take a sample by regulation in Denmark. But we then select the points where we take this sample so it reflects the quality best possible in our network. So not being the top floor of a high-rise building, we would never choose that point to take a sample, because it passes through entire pipeline network in the building and has nothing to do with us. So we take the samples as close as we can to our main system, but inside the building. That's what the Danish regulation tells us to do.
And maybe I can add to the question that as a supplier into the water sector, we have an obligation for our products that there is no smell, no taste, no color given to the water. And the same goes for pipes, for pumps, for valves, for everything. We have to prove that we will not affect the water quality in any way. Other questions? Yeah. No, I thought you were raising it. Yep, in the back.
Тут розповідали про цифрові рішення, про систему бенчмаркінгу. Якщо я правильно зрозумів, це є система розроблена бенчмаркінгу, куди підприємства заносять всі свої показники, дані, і потім будь-який орган влади і зацікавлені особи можуть переглянути їх і взяти їх з тієї системи. Тобто я розумію, що інших вже інформацію в якісь органи, підприємства дані не готують, не подають. Тому що в Україні кожне підприємство дає велику кількість звітів, заповнює показники і в податкові органи, в державні органи статистики, регулятори, міністерство. Це дуже багато займає і часу, і трудових ресурсів. І ця система би була для нас би дуже була корисна. Думаю, підприємства всі би хотіли використовувати, щоб було саме так, а не так, як зараз в нас побудовано. Тому прохання якось нашим органам влади пропонувати такий вигляд бенчмаркінгу, щоб застосовувати дійсно в нас, а не така система, як зараз діє в нас.
Yes. I can maybe answer the question from the water utility perspective, which I know of. So we have to report as larger utilities in Denmark into a benchmarking system on certain KPIs. For instance, like non-revenue water loss in our system, we need to report that. And there is an annual report where all these figures are displayed for all the utilities participating, which is I think around 100 or so in Denmark. So it's public available and displayed in the report every year. So that is, I don't think you directly can enter a database and extract the numbers, but you can see it at least once a year. It's published in a report.
And yeah, if I may add to that, thank you for the question. I mean, benchmarking and registers as a whole is something that we are trying to press and push for, so that the transparency level is as holistic as can be. In terms of the work that we have done with the authorities and the Environmental Protection Agency, again, it's not that we have created an online database for the public for you as an individual citizen to be able to go in and just extract. That will be the next steps. Of course, I think as more utilities they start to benchmark better and drives competition and tariffing, the level of expected transparency is going to increase. I think the point that I wanted to make in my presentation was that a standardized approach to all of these things that is fully digitally, that has a full digital solution that is not unique to one utility in one oblast, in one khoda, that makes things more complicated in the long run for you to do reform, to do to fulfill the requirements of the acquis communautaire, so that you are actually now at a super let's call it advantageous stage, where if you are serious as a country of working towards accession into the EU, that taking this standardized approach across all agencies and working with utilities, so you have public, private, but you also have private conversations. The utilities need to talk together, which I understand that you do in this what's called Ukrovodokanal association that has been organizing this. That dialogue needs to have its own forum where decisions are made on how to best make use of digital solutions that have been proven elsewhere. So you don't start building things up from scratch again and again and again and spend hours and money that we do not have on repeating things that ties you into one contractor, for example. It's about utilities and agencies also being able to do the work themselves, configuring platforms, integrations into national registers. And that's where something like we have in Denmark with the KPI benchmarking database comes in and is handy. So I don't know if that answers your question, but that's my view on it. So thank you. But where are you, which organization or association are you from?
Я про комунальне підприємство Тернопільводоканал. І зі сторони просто підприємства, як ми заповняємо, коли ви кажете стандарти заповнення одних і тих самих показників, але які можуть мати різні значення, тобто розуміти різне під собою, що цей показник означає, може в різних організаціях означати різні дані. Тобто тому, так як ви кажете, тут потрібно якусь стандартизацію і зменшення цих баз, щоб була одна база, щоб могли ці органи влади користуватися. Дякую.
Yeah, a great. Yeah. Thank you for saying where you're from. Very happy to have a dialogue continued on how to copy and adapt digital standard solutions. Thank you.
So maybe I can add to the answer. The way I keep myself updated on what's going on in the Danish water sector is that I enter into the Danish Water Association. Every year they publish a publication called Water in Numbers. And there I can see all the utilities above a certain size. I can't exactly remember where the threshold is, but there I can see their non-revenue water level. I can see the energy consumption per cubic meter of produced water. I can see how much it costs the water utility to produce 1 cubic meter of water. And the same goes for wastewater. I can see exactly the same numbers. I can see burst frequencies, etc., etc. So I enter the platform of Danish Water Association, and then I take all, and they are public available, so everybody can go in on that website and collect this document. But I guess also the question is about, are you cheating? Or can you cheat? So you simply give good numbers just to shine, or is it so transparent that I almost say you can't cheat?
Basically, it's probably a matter of trust, because there's no real control mechanism in place to test if we do it right. But there is always a certain uncertainty to data. So you cannot say for sure that it's free of any kind of error. But I would say deliberate cheat, I would say probably not. But there's no control mechanism, I would say. Basically, there's the Denver system and there's a government system, which are two different systems, but some of the indicators are the same.
I think just reflection. I mean, who knows? We might see a bunch of auditors in water audits of KPIs and benchmarking. That might be the next thing that we have to consider. Just like you have with ESG reporting now, which is so incredibly stringent from CSRD directives, where you do have an army of consultant auditors coming in and checking non-financial data. I could see that might be the next step if we do consider it from the aspect of cheating deliberately or falsifying or misrepresenting data. So we might come after you.
Yeah, but basically we are subject to external audit in a number of places. Financial audits for sure, that's mandatory by law. But then again, as utility, we are also certified according to a number of ISO standards. And that's also, if you are to be certified in the ISO system, you need to have external audit on a big number of topics. So we have a number of people every year that comes into from external audits that comes in and looks at many parts of our operations.
Okay, thank you. Any more questions? Okay, so just to sum up, this morning we started with where the water comes from, groundwater protection, groundwater management, water quality. And then we moved into, say, the distribution network. We were talking about non-revenue water. We were talking about DMA technology. We have been talking about pressure management, leakage management, or finding the leaks. And now finally, we have been talking about digitalization. I also maybe should mention, if any questions arise in your head afterwards, you will find us in the exhibition area, just in front of the coffee and cake delivery. We have a Danish pavilion, and all the companies or all the people here have given speech to you today will be present there, and you can go there and ask more detailed or look and feel of different products. And then tomorrow we will continue with wastewater. As I said this morning, wastewater should be seen as a resource, not as a problem. So we will talk about how to collect the wastewater, how to clean it, and how to utilize the waste or the sludge to produce energy, to produce biogas, maybe also adding to the district heating system. So thank you for now, and see you again tomorrow, hopefully. Thank you.